Okay, welcome everybody to the second session of the conference. We hope you had a great time yesterday. We're really looking forward to the talks today. Before we start, very quickly, I just want to remind everyone that we'll be using Slido for the Q&A, but also you can use Slido to post questions for the discussion sessions on Wednesday and Friday. So for the Q&A, this is the room you have to use, but if you click here, you can choose Wednesday or Friday. You can do this throughout the conference. It doesn't need to be specifically during the discussion. You can do it today, tomorrow, and just feel free to submit a few questions if you want something to be discussed during the discussion sessions. Once you're done, just remember to come back to the Q&A room so that people can, when you submit questions, they go to the speakers. I think that's all. I'm gonna handle over to Inga Kamp now, who's the chair of today's session. Inga, it's all yours.
Thank you very much. I second this. So I really enjoyed the day yesterday with the talks, but I also enjoyed especially the short talks that you could watch online via YouTube. So I already went through a couple of them, and it's actually super great. So I encourage everybody to go there and check out the posters and the contributed talks. So having said that, we come to our first invited talk, which is by Barbara Ercolano from the Ludwig Maximilian University of Munich, and she will talk about disk evolution and dispersal. Barbara, the floor is yours.
Thank you very much, Inga. I will start off by sharing my screen, hopefully. And actually how I really start off is by thanking the organizers for having put together this mammoth conference. So I noticed there are really a lot of participants also during the live sessions. So it's a really great pleasure to be able to tell you something about disk evolution and dispersals. Although of course this is a huge topic, and there will be many areas that I will not be covering in this short, even 45 minutes review. Just to give you an idea of what I will be covering and why we care about the evolution of protoplanetary disks, and in particular about the very short time in which they finally disperse. That's because, of course, we want to know something about how planets have formed. And of course, we had a brilliant review yesterday from Didier, in which we see how we find the planets and what we learn from them. But there was a hint of skepticism about what we can learn from looking at disk about the planet formation process, because this is so complex and there's a lot of randomness to that. Of course, I second that as well, but I am also optimistic that in fact we are improving a lot in our understanding on how the first building blocks of planets may come together and how the young planets evolve inside, let's say, the womb, the mother place, which is the protoplanetary disk. And in this very simple graphic, I just showed small dots and large dots to basically signify the beginning of the very large journey in orders of magnitudes that the small dust grains which are present in this protoplanetary disk have to go through, from micron sizes all the way to hundreds of kilometers. And in all of that, of course, they're aided by a nice, dense environment of the midplane of the protoplanetary disk, but they also have to deal with a lot of complex processes that go on, some of them which are seen as disturbances, some of them which are probably aiding the formation of the planetesimals and then of the planets themselves. First of all, we know that the disk is not just sitting there doing nothing and making planets. It's actually sitting around a very young active star. And by active star, I don't mean a specific type of star, I just mean a young star. All young stars are very much more active than old stars. just like people. And in fact, if you look at the surface of our sun now, you would say that's pretty active. But actually, a young sun, when the sun still had its disk, you would have seen 10,000 times more activity. In fact, these young stars are able to emit 10,000 times more X-rays than the sun does today. About 1,000th of their bolometric luminosity comes out in very high energy in X-ray wavelengths. And why this is interesting? Well, that's interesting because X-rays, unlike extreme ultraviolet radiation, for example, they don't much care about hydrogen, and so they can penetrate much deeper into the midplanes of the disks, or very far into the atmospheres anyway, and they have strong influence on the chemistry inside the disk. And this is, of course, the material that then ends up into the planet and onto the planet at later stages. And so again, from Didier's talk, if you think about we need to start looking at how the building blocks of life come about. Well, these building blocks probably have had to gone through quite a lot of history inside the disk and on the young planets, which involve also the strong irradiations from these very young stars. And so there's a lot of work to be done to see what complex chemistry can happen due to this irradiation inside the disk and at the later stages. One important thing also that the X-rays do to the material of the disk is that they ionize it. And this is interesting because an ionized gas, a charged gas, can see a magnetic field, so it's coupled to a magnetic field. And the level of ionization also has an input on the level of coupling that you have between the gas and the magnetic fields that might actually thread the disk. Until a few years ago, one would have said, yeah, this is really important to understand the areas of the disk where magnetorotational instability can work, and this is how we thought that the disk could accrete. So we thought that magnetorotational instability would work in most parts of the disk apart from the dead zone, and this would create this viscosity and would allow to redistribute angular momentum within the disk, allowing that mass to flow inward. Well, the picture might be changing recently as a more complex magnetohydrodynamical simulations, we also take into account non-ideal effects, find that it's actually really difficult to make MRI to work in many parts of the disk, apart from the very inner part. And then in fact, angular momentum might not be redistributed by this process, but might be extracted from the disk via outflows, MHD-driven outflows that might actually just extract the angular momentum from the disk, which has, of course, different consequences on the surface density evolution of the material within the disk. All of that is also controlled really by the level of ionization, so from the radiation from the central star, that basically tells you what resistivities are then relevant where in the disk. The other thing that X-rays do, the soft part of the spectrum delivers heating to the atmosphere of the disk, is able to also unbind parts of this disk, so that some parts of the disk through X-rays, through FUV radiation, maybe also through EUV radiation in parts of the disk, they achieve a temperature that is then higher than the escape temperature locally, and they are unbound. And then this material in the atmosphere is accelerated away by the centrifugal force in what we call a photoapparative wind, which is what we believe, at least in the last stages of disk evolution, is then leading to the final disappearance of the disk. What's interesting is all of these processes basically happen on similar timescales, and so it's interesting and also makes the problem a little bit more complex, because you have to try at least to take everything into account in some kind of self-consistent manner. And as I said already, as a disclaimer at the beginning of the talk, there are many aspects of disk evolution that I will not be covering here, in particular anything to do really with simulations and hydrodynamics and many different types of hydrodynamical instabilities that can happen in the disk, VSI, MHD, non-ideal MHD. All of these are things that are very relevant to planet formation and to the evolution of the material in the disk. But luckily, there are many contributed talks that talk about them. And so I have looked at a few of them. Two that I would like to highlight now are those of Mario Flock and Moon and Gong's talk, which specifically look also at the inner parts of the disks and what is happening there in terms of MHD processes. And so if you look at this picture here, you already think, okay, well, Didier yesterday had it right. This is really too complex for theory to really say anything. Well, this is why it's important to build models that can then be tested against observations. And indeed, in terms of observations, the reason why we're sitting here, well, not in Chile, but in our in our rooms, pretending to be in Chile, is because we have these amazing new observations from ALMA, for which, of course, we already seen many times the WOW image, which this was the result of Laura Perez poll yesterday, which of course tell us a lot about the structures of the disk. For the first time, we can peer inside those structures and have a snapshot of specific disks at a specific time. And that's, of course, interesting and is showing also that many disks, at least all the ones that are being imaged with ALMA, show some kind of substructures. And there's, of course, talks in this conference, including a review talk by Andrea Isela, that concentrate on this very important aspect that ALMA has helped has made, which is these structures, which are very likely, at least some of them, a result of the interaction of planets with the disk material. You can also look at Jeff Jennings' contributed talk, where he actually uses super resolution of the D-sharp images to show that there's even more structures that we think at even smaller scale than we think. So this is all very fascinating and definitely something that has motivated many theorists to go and try and explain the origin of these morphologies. But when we talk about global disk evolution, we have to be careful that we are now looking at snapshots in time, and we are also looking at the subsets of disks which can be imaged to such a resolution, which is not all of the disks. We have actually, before ALMA, also learned something about disk evolution by looking at global populations and disks and how they evolve in their boring, unresolved photometry. And so this is one thing that we have learned, is that disks are relatively short-lived. So this plot probably, as everybody has seen it in different version of it, in which basically what you do is that you look at how many stars in a particular cluster, which you take as a simple stellar population object, so all the stars have the same age and the same metallicity. Then you can look how many of them still have the disks. You know the cluster age to a better, precision than you would know a single object age. And then you can say, okay, if you look at these points, you get to about 10 million years anyway, nobody has any disks left. And if you take these plots and all these points at face value, you come up with basically these time scales of 2.5 million years. On this topic, there's also a very interesting talk that you can look at by Arnaud Michel, who is working with Nienke van der Mare, who looked at the effect that external photoevaporation from massive stars can have in causing the early demise of some of those disks. And if you do that, then some of the points down here in these plots are taken out because of they are in regions where OB stars are present. And so you could say that I think it makes a very convincing argument that perhaps this timescale for quiescent regions, for regions without OB stars, this timescale, the survival of disks is a little bit longer. Anyway, you still have a disk that lives for a few million years. And that is a first time scale that is relevant when we talk about disk evolution, the global disk lifetime. How long does it take for a star to go from disk bearing to diskless? However, there's a second time scale that is relevant if you want to understand disk dispersal, and that's how long does it actually take to disperse? Disks are dispersed. Are they dispersing all the time from the second in which they're born at the same rate until they're gone? Or is there some process that switches on and then removes the disk quickly? We know it's the second now. And the reason that we know that, again, is from, let's say, boring photometry by looking at the color diagrams of disks. So here you see for Taurus, this is the work of Kevin Luhman, in which if you plot the colors of disks in the K-8 and K-24 band, you see that disks, primordial disks, are all up here. So they're very bright in 8 and 24 micron colors. So this is warm dust in the disk that is emitting at this wavelength. Once the disk has gone, what you're left is just with the emission from the star. So you just have the K emission down here. And what you would expect is that if the disks are just homologously depleting at all radii, slowly just draining onto the star, but with effect of some kind of viscosity or accretion onto the star, then you would expect to see many disks in this transition phase here following this line. And you don't see that. You see that there's a few objects that say they bridge this population and that population, and they seem to follow a different track. And so if you interpret this two-color diagram very simplistically and say, okay, 8 micron is coming from warm dust closer to the star than 24 micron emission, then if you follow that track onto the plot, which is basically down and then to the left, it means that you are becoming less bright in 8 micron and then in 24 micron, which basically means that you are removing the dust from the inside out. And this was indeed taken as a motivation of developing models that would disperse the disk from the inside out. So you see, the other thing that you see from this plot is that there's not a lot of objects in transitions. So those objects, which we will then for now name transition disks. So these disks that are in transition are roughly of the order of 1/10 of like the global disk population. You can debate on this number, but we are more or less there, which basically tells you that if every disk has to go through the transition phase, because every system has to go from being disk bearing to diskless, then if you only see 1/10 of the total population in this phase, it means that this phase must be rapid. And so these objects are rare because they are shorter lived. And so this is the second time scale that I was talking about. And indeed, you can check this by running lots of aridity transfer models, and you will see that you come up with these regions in the color diagram in which the inside out clearing has a very specific path. And you can do the exercise of comparing this with all the stuff from your region that you can, you have the patience of collecting. And then you see, at least we convinced ourselves in a series of papers that the evolution of these disks was indeed from the inside out via the formation of so-called transition disk. So a disk with a central cavity. And so we don't see this, disks just slowly evolving from being optically thick to optically thin, but we see this, disks doing nothing, being optically thick for a few million years, and then dispersing and being left as photospheres or just debris disks. And in rare occasions, about 10% of the occasion, you see these transition disks. Now, remember that all of this was kind of worked out before the WOW image, before ALMA. And so we thought that all those disks with cavities were a result of this dispersal. And so we just basically, as a community, were motivated to produce models of this dispersal that would have satisfy these two observational criteria, which is first, that the disks disperse from the inside out, and second, that you have a process that lays dormant, quasi, does nothing for a few million years, and then suddenly it removes the disks very quickly in about a tenth of the global disk timescale. And that's roughly what a photo operation can do. And indeed, in this very simplistic picture that I give you, where you have a disk which is accreting, so mass is moving in and angular momentum is moving out. If you assume that accretion is going through a viscous process, or maybe angular momentum is going up if you have disk winds. In any case, you have a mass flow through the disk. You have the irradiation, you have photo operation, and photo operation has a rate which is roughly constant throughout the disk lifetime, unless it's driven by FUV processes. And in case it isn't, it's roughly constant throughout the first 10 million years of the disk lifetime. And you have an accretion rate that decreases with time. So at some point in the disk lifetime, the wind rate will be winning against the accretion rate. And so the wind will be removing mass faster than accretion can fill it back in. And so you have the development of a gap inside the disk. Now, this is now a photoevaporative gap, which is very different from a gap dynamically sculpted by a planet in the disk. And the main difference between the two is the fact that once you have a photoevaporative gap, there is no connection between the inner disk and the outer disk. Material cannot flow past the photoevaporative gap, because as soon as it reaches the inner edge of the outer disk, gets photoevaporated away and centrifugally accelerated out. So it cannot land on the inner disk. Instead, when you have a planet, you have material flying over the planet to the inner disk at a reduced accretion rate, of course, but you still have this connection between the inner disk and the outer disk. And so in the presence of a planet which has made a gap, you can still retain an inner disk for a very long time because you keep feeding it. In the case of photoevaporation, the inner disk drains onto the central star on the viscous lifestyle timescales, which is given by the outer edge of the inner disk. The outer disk then is basically done directly irradiated and then evolves from the inside out. I would say that the whole community for this dispersal for photooperative models agrees on this broad brush picture, and there's now many models that have been made with different techniques. And I will not go into the details of all that, and I will not even give you an opinion of what can be done better or what can be done less. So different people have used different approaches, and unfortunately they come to different conclusions. So the broad brush picture, we agree, but the wind mass loss rates differ sometimes by 2 orders of magnitude between amongst these different models. And also the wind profiles, so where the wind is able to remove mass from, is also very different. And unfortunately, these differences are very important for the purpose and scope of developing this model. What is the purpose and scope of developing this dispersal model? The purpose and scope is to understanding what is the effect on planet formation. And in particular, so if you want to make population synthesis, you need to have a way of removing the disk. And if you change between these different models, you get different answers also for planet formation. And so it's important that we get this right. Just to give you an idea of some examples of how important it is that we get this right. There has been already basically 18 years ago, Andrew Yoden and Frank Shu, in the paper on the stream integral stability, they mentioned that, suggested that photoevaporation may help the streaming stability, may help achieve the conditions in the midplane for streaming stability to occur by removing gas from the disk atmosphere, which is naturally dust poor. On top of that, large grains cannot be entrained in a photooperative wind, as I will show you later. So basically the effect that photoevaporation has is to locally enhance the solid to gas ratio, which is what streaming instability needs to form planetesimals. When we tested this idea with the photoevaporation models, we got to completely different answers depending on which photoevaporation model we used. For example, if you use the FUV model, which is able to remove large amounts of gas from the outer parts of the disk, then you see that you can make quite a lot of planetesimal quite quickly and at very large radii in the disk up to 1000 U. If you do exactly the same model, but you switch the photoevaporation profile to the XUV profile, you say, no, you get a different answer. You make only a few planetesimal, look at the difference in the scale here. I'll make only a few planetesimals about Earth mass, and you make them very close in to AU. So you would come to the opposite conclusion that actually this process is not relevant to the making of planetesimals. If you're interested in more talks about the streaming instability, how robust it is to different processes in the disks, do take a look at Daniel Carrera and also Jake Simon's talks, which are on the YouTube. And so what we've done here, we just basically switched the profiles and got different answers. We also did the same thing later on when we tested the assumption that photoevaporation may provide a parking radius for migrating giant planets. This was an idea which was put forward by Richard Alexander and Ilaria Pascucci in 2012. And we tested it further by looking at how sensitive this process would be to different profiles that we knew at the time. And we found, of course, that just simply switching the profile, you got completely different final distribution of the orbits of giant planets once you made a population. And again, if you switched again the profile to an FUV profile, you got something else again. So to cut the long story short, these are not details that we don't agree on. It's just the meat of the subject that has to be worked out. And because of the complexity of the physics that goes into it, and also on the necessary shortcuts that have to be taken in the simulations, the only way to move forward is really to pay more attention to the observations and constrain the models with the observation. This is something that has been done, is starting to be done systematically now. For example, since photoevaporation is also a key ingredient of planet population synthesis code, you can check by taking a planet population synthesis code, like, for example, that from Christophe Mordazinic's group in Bern, and you look at the disk statistics that you get out of these models, you compare it with observations, and you see the photooperating disks in these models are here. And in fact, the observation tell you that they should be here. And so here already you can see, okay, then the photooperation model that has been implemented in this code is maybe too weak because it removes the disks when they're already too low mass compared to the observation. This is just an example of the things that you can do. Of course, you can also look at Christina Monch's talk who is also trying to look at population planet statistics to have a hint of what may have shaped the dispersal of the disk at early times. Of course, the best way would be to look at those winds directly with some effective line diagnostics, invert the line diagnostics, and tell where is the wind coming from the line kinematics, and also tell what is the density, the structure of this wind. Unfortunately, we haven't been able to do that quantitatively yet, but we are really, I think, on a good track, particularly using forbidden lines I'll show you some examples of that. So the Neon 2 line is a line that already in an early survey by Ilaria Sterzig, one sees that there's a clear hint of a wind in this line, since it is slightly blue shifted. So this line is produced in material that is slowly moving towards us. If this was a jet, you would see like 100 kilometers blue shifts, but you see only a few kilometers. So this is a slow disk wind, typical of a photooperative wind, but also maybe an MHD wind. And so a lot was done with this line, and the photo operation models at the time were very successful in reproducing this line, but maybe too successful, since you were able to reproduce this line with models which had about 2 orders of magnitude in the mass loss rate. So I won't go into the details of how this is possible, but it is like this, and basically this tells us that the Neon 2 line alone is not very useful, but you can use it in combination with other constraints. For example, from the free emission, this was also an idea from Ilaria in 2013, and we checked it also with James O and Anna Skyfe for some objects in 2013, where basically you look at the free emission, which you can clearly see above the dust emission, and what you see is this is a measure of the ionization in the gas. And then you can compare it with the photo operation model that you need to match your Neon 2 line and see whether the two measures correspond to each other. And this has been done, for example, for TW Hydra. In the future, we might even be able to resolve the free emission that might be coming from a wind, for example, using the next generation VLA. So this is a really exciting idea or prospect, let's say, that we might be able to see the ionized part of the wind in a spatially resolved fashion. We have made some calculation together with Luca Ricci and Sarah Hatta, and we see very different predictions for photooperative models of different mass loss rates, so different X-ray luminosities, as you see in the left panels. And also we see that we have made a prediction with a very simple-minded MHD type wind, and we see that we have very different predictions. So one might be able to use this model. So this is, if you just look at the surface brightness now, we might be able to use these observations to look at the nature of the disk winds in some of the objects. Another line that was used, and this has been a lot of work on, is the Oxygen 1 line. And here I have an historical figure here from the Hartigan paper, in which it was already seen that basically this line has two components, a high velocity component, which is coming from jets, but also a low velocity component, which is slowly blue shifted, which is typical of a wind. And again, this line tells you something more, because it tells you that the wind must be quasi-neutral, so it cannot be fully ionized, as for example would be the prediction of an EUV type wind. And it can be quite well matched from photo operation models. We were sure of that in 2016. So we wrote a paper which said that the Oxygen 16300 is the smoking gun of X-ray photo operation. And in the paper, there's no question mark. But I put a question mark now, because about a few weeks after the paper was published, more observations came out at higher spectral resolution, in which they showed that this line is actually two lines, has clearly two components, and this broad component cannot be reproduced by a photooperative wind. And this, in fact, very exciting discovery, which might point to the presence of an MHD type of wind closer into the star. And in fact, one possible explanation would be that, in fact, the different line profiles show some kind of evolutionary stages of winds, of outflows, in which with young objects you have MHD disk winds close to the star, giving you this broad component, and as you move to transition disk objects which have lost the inner disk, then you're only left with a narrow component from an outer wind. Now, the nature of this outer wind is also debated. We have been able to fit it quite well with photooperative models, and we have been able to fit the broad line, the broad part with a very simplified MHD models, and in the joint profile looks a little bit like the observation, but it's very much dependent on the model inputs. And so we hope to do this now for a large selection of objects which have been now collected by many groups, including Ilaria Pascucci's group, and this might tell us more about what wind is relevant when in the disk. Also, please look at Emma Whelan's talk, which shows other techniques that can be used to study the origins of the emissions for the forbidden lines. So one other possibility that we thought about, but I don't know, maybe this is something that it would be nice to discuss on Wednesday, is whether it might be possible to look at this, detect these winds in the dust emission. So Raphael Franz, a student in my group, calculated the dust entrainment in the photooperative winds and made some predictions for different assumptions of how well populated the disk launching region is from dust grains. If you have a well populated disk atmospheres, but for small grains, you don't need to have the large grains there, but micron-sized grains, then you do expect to see quite a strong wind emission in some cases. Whether this has been seen or whether these V structures that we see in the in some of the scattered light observation or in the MY loop observation, or sometimes you also see some kind of nebulosity above these disks. This is a question that I have now for the scattered light people here. There must be quite a lot. We will also see, please, the Antonio Garuffi's talk, and it would be nice if we could think together about whether some of the observations that we already have at the moment might show a hint of a few particles hovering above the disk surface, which would be very, very interesting. So clearly, if you want to understand disk dispersal, you should be looking at disks that are dispersing. And so we should be looking at what we thought were transition disks. Now, this is easier said than done, because it turns out that we actually don't know what transition disks are. At least I don't. Maybe I will do that. I will know that after the discussion on Wednesday. But at the moment, I am pretty confused. So transition disks are classically disks that were detected because they had a dip in the mid-infrared if you looked at the SED. So that if you think of that diagram that I showed you before, where the 8 micron dust is close to the star and then the 24 is later on. Well, if you see a dip at the wavelength at which dust of a certain temperature is supposed to live, then it means that this dust is not there, or there's less of it. And you basically, at the time with SED modeling, you said, okay, this dust is only starting at, let's say, 15 AU, and there's no hot dust closer into the star. This is not like all of the disks are now detected as transition disks. Of course, you now also have spatially resolved observations in which you clearly see cavities in millimeter grains. And now, when you make plots like this, you just put all of the observations together, and you don't know anymore what's what, until Ilaria made some very nice different symbols around these plots to basically show the different type of detection methods. But the point that I want to make here is that if you look at the accretion rate detected onto the star for many transition disks and compare it with the size of the inner hole, these dispersal models can only really reproduce this type of disks. So this area here, basically these gray lines that you see at different model tracks. See, there's no way they can reproduce what we call type 2 transition disks, which are disks with large cavity and high accretion rates. So these were the typical candidates for having cavities made by planets. And in fact, if you look at Nink's talk, she's also suggesting almost a different disk evolution and a different, let's say, paternity history in terms of what kind of planets can be made by type 2 and type 1 disks, or protoplanetary disks that are compact, or those that have structures and are large. And indeed, I would agree, and also this was also the idea of James Owen and Clyde Clark in 2012, that we are really looking at two different populations here when we have this plot. Type 1 and type 2 transition disks might actually have different physical origins. If you look at many of the type 2s, are these kind of guys with very large millimeter fluxes, which have been observed by ALMA. And Paula Pinilla did the exercise of comparing, looking at the SED of some of those with clear cavities. And if you look at the SEDs, and if you didn't have ALMA, you would have never said that this was, for example, a transition disks. So the transition disk should look like the blue line in the SED. So this is an SED model that would fit the millimeter part for that hole. But you see, it doesn't fit at all what you see in the SED. So this basically is telling you that you have a lot of material close to the star. You just don't have the millimeter grains. And so there is some kind of filter, some kind of trap that is keeping the dust, the larger particles away. And so you can also look at these two talks by Logan Francis and Brody Norfolk, which talk a little bit more about what might be happening in the disk. So the point that I'm trying to make here is that these disks, this type 2 transition disk with large cavities in the millimeter, might actually not be objects that are really in transition. They might just be objects where planets have formed and they're keeping the dust away, but they're not actually transitioning anywhere. And so here's my poll now, my question to you guys. You know now what I think, but what do you think? Do you think that this type 2 transition disks, or the disks that have large cavity and high accretion rates, do you think that these are really transition disks? So they are objects, they are in the rapid transition phase going from class 2 to class 3? Or do you think that they might actually not be transition disks? So be disks that are actually long-lived, but they are rare. So there's only 10% or less of the order, because they need to have a large planet formed in them, and there's not that many. And so long-lived and rare objects, or rapid disks in transition from class 2 and class 3. So if you have an opinion on that, I'll be interested in hearing it. So you can answer this poll by entering Slido and using the code HLTAU 2020, like you did also yesterday for the other talks. So those objects, however, even if they have planets in them, those type 2 transition disks, they're still being irradiated and they're still being photooperated. So for those objects, there's actually quite a lot of nice interplay between the winds and planet formation that needs to be explored more. What we know until now is that obviously the planets would reduce the mass flux into the star. And so photooperation may be able to act quicker than usual. So they might really have, these objects, a different evolutionary track that once than the disks where planets didn't form early, or at least when giant planets didn't form early. And this is an old simulation done by Giovanni Rosotti during his thesis, in which he basically did Fargo simulation, put in a giant planet in, and showed that photooperation would occur on a much shorter timescale, clearing the inner disk of dust. And indeed, there might be objects in which this might be happening. For example, TW Hydra also has a clearance in the inner part, which might be the beginning of a photooperation gap, and has clear gaps further out, which might be the planet caved gaps. Of course, this is just one interpretation of the many for these objects, but it's something that tells us that we should look at this interplay a little bit more detail. Now, the usual question is, if all of those type 2 transition disks have planets, and we have been desperately looking for planets, also you heard in Laura Perez's talk yesterday, we are getting better at finding them, but still we don't find that many. But I think this is not surprising at all. Probably most people could have said it without doing 3-dimensional simulations of, of planets embedded in disks like we did. There's simply a lot of material that is falling onto the planets. And so unless the planets are very large and they can open a very clear gap, then a lot of the emission from the planet will be absorbed out simply by the large amounts of material on top of the planet. And the same if you also look in H-alpha. Judith Szilagyi and I found also that it would be very difficult to detect H-alpha from embedded planets unless you have really huge planets inside the disk which have opened a clear gap. Okay, so my conclusions now are, I leave them here, but these are more like points for also discussion. These quints drive the dispersion and probably also the evolution of the planet forming material. And depending on the nature of the wind, they might do that at different times in the disk evolution. You may have young disks with MHD winds close into the star, or maybe even acting on large radii. This is something that still has to be explored. But the latest stage are probably controlled by photoevaporation, was removing the outer parts of the disks. Unfortunately, we don't understand this process quantitatively yet. We do not have profiles that agree with each other. And so we do need to do more testing of those models, comparison with the observations. And indeed, models are becoming now predictive enough so that we can compare it with spectroscopic observation. Wind diagnostic studies are definitely gaining pace. The next frontier, I would say, is to now start looking at what is the interplay between planet formation and disk evolution. Also, in terms of looking at the effect of the of winds on for example, on the accreting material of the planet, or perhaps onto the migration speed of a planet inside a disk that is photooperating. And so, with these points, I would like to stop. And I'll be happy to take your questions. Thank you.
Thank you very much, Barbara. This was a very, very comprehensive talk. So I see lots of questions, actually. And maybe we start with one quick clarification question. So what I see here is a kind of ambiguity. People are not really clear what you define as H0. So disk lifetime is some mega years, but how do you define H0?
Yeah, well, this is a question that, oh, sorry, I just somehow, this is a question that, again, I think is arbitrary in the sense that age 0, when we talk about ages, as I said before, in general, we are taking the age of the cluster in which the disks were taken. So when we, I think this is something that perhaps also Ilaria will talk about later, a lot of the disk statistics and the disk demographics are done by looking at disk populations within a cluster, which is a simple stellar population. And so the age of the disk is basically the age of the cluster. So that's how it's in some way defined.
Okay, thank you. And then staying a little bit with,
okay, yeah,
staying with age and evolution. So maybe two linked questions, but are transitional disks really a necessary step between the protoplanetary disks and debris disks, or are there any other evolutionary pathways that lead from one to the other?
Well, there has been the suggestion, of course, that disks might just simply evolve and viscously drain onto the star, so become progressively optically thin at all wavelengths, since they're becoming progressively optically thin at all radii. However, we don't see any evidence of that, in particular because if you think about it, if you think about a viscous process driving this homologous depletion, then you would expect to see most of your disk population in the transition phase, since it would take longer and longer as time goes on, basically to reduce your surface density. And so you would expect to see the majority of disks being transition disks and going between optically thick and optically thin, and you don't see that at all. The other thing that that's also gaining pace recently is that in star forming regions where you have O stars, you might have disks which are being removed from the outside in, almost by external photo-operation, so by radiation from external stars. Now, that is something that would be interesting to check. Again, you could do that in that color diagram if you could get the color of those populations, because in that in those typical sources, then you would expect to basically lose the 24 micron first and then the 8 micron, and then you should be able to see the opposite track. Now, I have never seen objects population doing that, but it's also true that all the data that we collected at the time were for regions without OB stars. So it would be nice to actually look at that to see whether this is really a relevant process for large populations.
So James Webb may be able to do that, actually.
Yeah.
Okay, thank you. I see another question, and again, it's two questions that are very closely linked. How many observed gaps are actually photoevaporative gaps? And here you can think of, me or.
Oh, sorry, I don't hear you anymore.
Opened by a planet?
Sorry, I lost the last minute. So you said how many gaps are really photooperative gaps, and then after that you were gone.
Yes. And then, if you find such a gap, how do you distinguish between whether it's opened by a planet or opened by the wind?
Yeah, that's right. So that's a very good question. I don't have an answer for it, and I don't think anybody does have an answer to that. So one suggestion that has been also driving many observing proposals was to actually try and understand how much gas there really is inside the inner disk, and see whether you can reconcile it to photooperative models, which do predict there will be times in which in which you expect to have an accretion signature onto the star. So you expect to have some gas into the inner onto the star, but this will be relatively short-lived time. The thing that you can do, of course, is also look at the shape of the gap itself, and there are predictions for that. The shape of a photooperative gap would be different than the shape of a planet carved gap. But even that is a little bit difficult, because you would need to look at specific wavelengths. And now there were suggestions to say that, well, you expect basically a pressure bump inside the so at the edge of the outer disk for planet gaps. But actually, when we checked, we also expected for photooperative gaps at a slightly different place. But the differences that we found, at least from the theoretical models, were so small that I doubt that you would be able to see that from the observations. So I guess it is difficult to say that. The other thing that you might be able to do is to actually just do energetics considerations. If you have a disk which is really very, very massive, and it has a very large gap with very high accretion rates, then I would say that in that case, it's very, very difficult that this would be a photooperative gap, simply because at least all models of photooperation at the moment, even the ones that are completely cranked up in terms of X-ray luminosities, they don't have, you don't get wind losses, wind rates, much larger than a few times 10 to the minus 8 solar masses per year. And so if you have an object that is accreting at 10 to the minus 8 or 10 to the minus 7 and has a very large gap, then you may ask yourself, why should photoapparition have opened this gap, since accretion rate is much stronger than a possible wind rate. But of course, we could be completely wrong on the wind rates. And this is why it would be nice to actually be able to find the diagnostics that tells us what the wind rate really is from observations. And then you might have a much better handle on it.
So if I understand you correctly, those are the type 2 discs, no? The ones with large cavities.
That's right. The type 2
high mass.
Very difficult to obtain with photooperative models. The only way that we managed to do that, and I didn't show this in this plot, is by assuming carbon depletion. Now, there are some observations, many observations that show that a lot of the carbon is sequestered out of the disk atmosphere. In this case, Lisa Wolfer made hydrodynamical models in which shows that in the case of a carbon depleted gas, even by depletion not only a factor of 3, you see much higher wind rates, and you see also a profile that is pushed to the outer parts of the disk. And so those objects could almost be explained by enhanced photooperation in carbon depleted disks. However, where you can explain a population of them, this is something that Lisa is looking into at the moment, and we hope to have an answer later. But of course, it would be very nice to know what are the limits of the photooperative gap. But still, this doesn't answer the question, because you could have a gap in an object that has an accretion rate, which is okay for photooperation, and an inner radius that is okay for photooperation. You still cannot be sure whether it was photooperation or not. So I guess you can only say for those objects where photooperation can be excluded, but you can actually say it was photooperation unless you do see the wind. So unless you have also these line diagnostics and you can match them, because line profiles do look different for transition disks. So they do look different when the material is being basically photooperated away from the edge of a disk. And so this is something that would be interesting to see.
There was actually a question on the line profiles by Chris Johns-Kroll, and this is about the broad component of the oxygen 16300. It seems to be centered in velocity, but the question is, should it not be blue shifted?
It is
the broad component.
Yeah, so if you look at the large data sets that Ilaria and also her collaborators, Andrea Banzatti, have put together, this broad component is also blue shifted in many cases. In some cases, it's centered on the star. In some cases, even redshifted. These are still understood how this is possible. But in most cases, it is blue shifted. And the blue shifts are, let's say, rough, also a few kilometers per second. But the reason why this component is very difficult to be reproduced with a photooperative model is not the blue shift, rather is the width of the broad component, which suggests that the emission radius is much closer into the star, inside the gravitational radius of a photooperative model. So it's very difficult to reproduce those kind of broadness with a photooperative model. And this is why it has been thought, okay, this has to be a wind that is closer in and inside, and ergo a magnetic wind, even though there is no reason to understand, there is no specific thing that says it's a magnetic wind, but at the moment we don't know of any other process that could launch a wind inside the gravitational radius of a photooperative wind.
There was another question also that pertains to these profiles, and that was what actually sets the velocity shift at the peak of the MHD wind. Does this tell us something about the vertical or radial position of the outflowing material?
So let's see if I understand correctly. So if you are looking at the profiles, and you are basically saying whether this is telling you something about the opening angle of the wind. I think that there is some indication of that, and indeed maybe Ilaria, even though she's not talking about this, she's the expert here, and there is some indication, and there was also a suggestion in the Andrea Banzatti's paper that this, indeed, if you looked at the broad profile, you would deduce and look at the distribution of them over those auto sources. You would basically look at the inclination. You would deduce an opening angle of 35 degrees, more or less, which is in agreement of what was suggested for MHD type winds. Now, what is still unclear is that this 35 degrees, for what I understood, is something that you see on the large scale and not necessarily at the base of the wind, where the wind is emitted, and more or less also where this line emission would be coming from, since this is a very hot line, so it has to be close into the disk, and it's not really sampling the large scale outflow as, for example, a molecular line would be. And so whether this 35 degree was a coincidence, or whether it's really saying something about the opening angle of the wind, this is something that is still unclear.
Okay, and maybe there's time for one last question. I see here what is type 2 transition.
Sorry, Inga, you were gone again. Could you repeat from the question? You were gone again.
A question by Nicolas Coelho, who asked, can type 2 transition disks be circumbinary disks instead with undetected companions, as was suggested by Daniel Price?
Yeah, so this is certainly something that people thought about for a long time. And so this was, people went out because the first large disk with a very large cavity did have a planet in there. So people did and went and did a huge survey of those disks, and actually did have a companion in there, and did not find it. Did not find it that any of those other large-scale disks were binary. Now, if they were not able to detect it, this is not something that I know, but I remember, so I don't remember who was giving this talk, but a talk at a conference in which basically it was basically put in as Murphy's law, the fact that the first disk to be looked at was indeed around the binary, and then every time that people looked again, this was not confirmed again. So I don't know if this is now the final answer of that, but certainly the current surveys that have been done looking for binaries inside these large cavity disks have not returned many.
Okay, thank you very much. I think we have to leave it here.
Yeah.
Thanks again for a very nice talk.
Thank you, Inga. Thank you for the questions.
Oh, thanks the audience for nice questions. So we move on to the second speaker of today, which is Ilaria Pascucci. Hello. And she will talk about disk demographics, so some more population studies of these disks, and let's see what we learned from there about disk evolution.
Okay, can you hear me well?
Yes.
Okay, thank you very much for the invitation, the opportunity to review actually these incredible new results that came out from ALMA surveys just in the past 5 years. So I tried really to have a comprehensive review, so really buckle up because there are many results that we are going to discuss. And also because of that, I decided that I wanted to make a couple of key points up front, just in case I'm going to lose some of you. So let's start with the first one, if I can advance my slide. Yes. Okay, and I think the best way to make my point here, which is about diversity, is through this animation made by Dan Fabrici. So what you are looking at are many, not all, multi-planet systems discovered by Kepler. And so the sizes of these circles are scaled by the size of the planets. The orbits are also to scale. And here you can see the solar system in comparison. These are only the rocky inner planets. And I really like this simulation because, you know, you see it yourself, this incredible diversity of planetary systems out there. But I want to encourage everybody to go beyond this and also look at some of the trends that came out from these surveys. And in particular, which is relevant for this talk, are trends with stellar mass. And here is just an example of occurrence rate as a function of stellar effective temperature, and what has been now very well established, that low mass M dwarfs seem to have more planets, low mass planets, within 50 days from these surveys. The second point I want to make is best made through this press release showing the WOW image from HL Tau. And the point is that I think we are learning more and more that the dust millimeter observations are probably mostly tracing some aspect of planet formation rather than the global disk evolution, which is a point that also Barbara made in her talk. And I think it will become more clear in future days through the talks of Pint, Andrea Isella. So I will make some of these points as well, but I think the structures are most telling here. But we need to keep in mind those structures when we talk about these demographics as well. I will also not review the class 1 disks because there is a dedicated talk to that, but that discussion of what the dust is telling us is also important in relation to the early stages, so something to keep in mind as well. Now, what are the questions that we can address with surveys? I think they are very useful because we can look at the entire disk population in star-forming regions, and we can ask which are the typical disk properties, what is the spread in these properties, and how do these properties depend on some other parameters we think we know relatively well, like stellar mass, environment, and age. And together with highlighting the ALMA surveys, I certainly want to also point out the parallel effort that was carried out through ground-based observations, especially the VLT X-Shooter has done an enormous work in characterizing the stellar properties in this region. So I will highlight those results as well. So this is the table that I put together for the review, and I was myself amazed by how much was done in terms of surveys with ALMA. And bear in mind, this is only for surveys at 1 millimeter. There are others that were done at other wavelengths, which I will highlight as well, because actually it is important to combine multiple wavelengths to learn more about these disks. A couple of things to point out. You see here there is a large range of ages for these surveys. They are ordered from the young ones down to the old ones. Also a range of distances. Resolution is moderate because we couldn't invest much time in doing hundreds of objects, as you can see here in this column. And also the sensitivity is modest sensitivity. I also want to encourage you to look at the talks by Sierra Grant and Sirk van der Wiska, who present 2 additional large surveys at 1 millimeter. So other interesting information about low mass and ALMA star regions. Another thing to point out is that most of these surveys were targeting already known disks. So these were objects identified through previous infrared surveys like the Spitzer Space Telescope, WISE, or even with Herschel. And only in a few cases, the fields was unbiased, and so there is a range of classes of objects that have been targeted. And I will discuss also what we have learned going into the class 3 regime. In terms of environments, you can see now that we have both low mass star forming regions and again a large range of ages that are covered, as well as high mass star forming regions. So we see what is the effect of environment in terms of some of the basic disk properties. For Orion, I also want to encourage you to see the talk by Nick Ballering, where he combines the original 1 millimeter ALMA survey with 3 millimeter data. And now you can see not only the dust component, but also start to see some of the free emission and some of the proplyds that were originally discovered with HST. So a very interesting combination with of wavelengths. Again, on stellar properties, some regions have been better characterized than others. So this is obviously biased towards the nearby low mass star forming regions. But again, stellar masses have been properly better characterized, and also homogeneous accretion rates, which we will discuss as well. Now, another point I want to make is, before discussing the main results, is that the distribution of disks, and in particular of spectral types and stellar masses in these regions. And I chose this histogram from the paper of Cazzoletti, where you can see the distribution of sources in different star-forming regions. And the point here is that they are peaked towards the low mass M dwarfs. And this really should not surprise anybody, because we know that the IMF in most star-forming region is peaked towards the low mass stars. But that's an important realization when you want to compare with the exoplanet population, because exoplanet surveys have been biased, or their interest, let's say, is mostly towards discovering the population of exoplanets towards solar mass stars. And because some of the basic stellar properties are stellar mass dependent, you need to take into account the bias we have in the disk surveys to properly make the comparison with exoplanets. All right, so what are the properties that have been inferred from these moderate resolution and sensitivity surveys? So I want to make the point through this gallery of disks that have been observed towards the upper SCO region. So the first one, the most basic property we are getting, is a measurement of the millimeter flux at some wavelengths, and even if we don't have a detection, we have an upper limit, which we can convert thanks now to Gaia distances in most cases into a luminosity, and then in a dust disk mass, some estimate for the amount of millimeter grains in these disks. For fewer sources, surveys have also targeted the CO isotopologues, and being faint, there are some detections though. And so for some of these systems, we can get also an estimate for the disk mass. For more of them, but typically for brighter disks, there is also an estimate for the dust outer radius. And for those surveys that have targeted the CO main isotopologue, there is also an estimate for the gas outer radius. So we will see how the two compare with each other, for instance. Then for those regions where stellar characterization was carried out in addition to the ALMA surveys, we can also study the relation of mass accretion rate and dust disk mass, and also disk mass and stellar mass. So we see how that works as well. And finally, for a very limited number of sources, given the moderate resolution, you can also discover large disks with large cavities like this one here in the panel. However, if you really want to have a good overview of disks with large with cavities or large gaps, I encourage you to see the talk by Francis and also the recent paper, Francis and van der Mahler, where they have a nice reanalysis, homogeneous reanalysis of disks with large cavities and gaps. So let's start by discussing the millimeter continuum and the dust disk masses. So we need to make some assumption to go from a millimeter flux density into a dust disk mass. And I want to discuss some of these assumptions. The first one is that we typically assume that the emission is optically thin. And if so, then there is this simple relation that you can use to convert your millimeter flux into a dust disk mass. But that is not enough. There are additional assumptions that need to be made. One is on the absolute value of kappa nu, the dust opacity, which is rather uncertain, I would say. What is a bit less uncertain is the behavior of the dust opacity as a function of frequency, which can be characterized through beta. And then there is a relationship between beta and alpha, where alpha is the slope of the millimeter flux, the flux at long wavelengths. So what we have learned from surveys that were carried out in the past, as well as from a more recent ALMA survey of lupus, is that alpha does not seem to change that much from disk to disk. So you can see the plot here showing alpha as a function of millimeter flux. And it seems that alpha is the same in different star-forming regions, as it is shown here. So this is to say that while we don't know very well the absolute value of a disk mass, we know better the relative disk mass measurements. Then the third assumption that needs to be made is in terms of the characteristic temperature for these millimeter grains. And what most surveys have done is to assume the same dust temperature of 20 Kelvin, which is motivated by studies of solar mass stars, disks around solar mass stars, regardless of stellar mass. Here on the side, you can see a plot showing that that characteristic temperatures, which is on the y-axis, can be actually very different depending on the assumptions that you made on the disk outer radius, which dominates the millimeter flux. So here there are two lines, gray lines. This one here is from a set of radiative transfer disk model in which the outer radius is kept to 200 AU regardless of stellar mass, and then you would expect a declining dust temperature with stellar luminosity. And the other line is for a set of models in which the outer radius scales with the mass of the central star, and in which case you would expect a flatter distribution. So again, most surveys have taken this constant value for the dust disk mass. So actually what you look at is the evolution of the millimeter flux in most of these surveys. On the optically thin emission, I think it is important to consider what is the impact of that assumption. So there is a paper already out there by Ballering and Eisner in 2019, where they did SED modeling of many sources in torus. These are just 3 examples. So now you don't rely only on your 1 millimeter flux taken by ALMA, but you consider all the other points that you have at other wavelengths. And what they have found, which is summarized in this histogram here on the right side, is that the analytic optically thin assumption that we made in many of these surveys is that is underestimating the disk mass by roughly a factor of 3. And this is the same result, a very similar result that is presented in the poster by Alvaro Ribas. So I suggest you to look at that as well. It's done in a different approach, very interesting one using a neural network, but the results is rather similar, and it's an important result. So we should keep that in mind as well. Now, let's go into discuss some of the trends that have come out from the now low-mass star-forming regions. So I decided to use this figure from Ruiz Rodriguez because here we have also the IC348 cluster compared to the other different regions that were observed previously. And these are cumulative distribution as a function of millimeter flux. And what you notice, and what has been pointed out also in previous papers, is that the millimeter luminosities, and therefore we infer the millimeter dust mass, is declining with age. There are a few exceptions that are also worth pointing out. So this is a cumulative distribution comparing Ophiuchus, lupus, and upper SCO. And Ophiuchus, while it's younger than lupus, appears to have a slightly lower disk mass population. The most extreme case is actually the Corona australis, because this is a young cluster, and still the population of the disks appear to be much lower in mass, more similar to upper SCO, you can see here. So another point to take away from these surveys is that perhaps we should consider also initial conditions. They can be different, and that will reflect in this distribution of disk properties. Now, looking at the high mass star-forming regions, I think there we also see the effect of the environment. So this is a plot of cumulative distributions for the NGC 2024. On this panel, the left panel, you see the east side of the region, and on the right panel, you see the west side of the region. And what is striking here is how on the east side, the dust population is similar to the young, low nearby star-forming regions, and instead on the west population, you see more depleted disks that have much less dust mass, more similar to upper SCO. And then the question here is again, do these different regions start with different population, or is it perhaps an effect of external photoevaporation due to the IRS-1 massive star that is in this region? I think the effect of environment is best seen in DONC. So let me show you those results. So this is a plot again on cumulative distribution in disk mass as a function of dust mass. DONC is in blue, and this is from an earlier survey by Eisner and collaborators. And the brown one is from a region that is farther away from the trapezium. And you can clearly see how the region that is farther away, surveyed by Van der Wiska and collaborators, is more massive. Now, although we are discussing dust disk masses, I think it's appropriate at this point also to look at gas disk radii in the same region, because they tell a similar story. And so this is the work here of Boyden and Eisner, also very recently this year, and you can see the gas radius in the trapezium as a function of distance from the ONC. And you can see this trend of lower gas disk radii, smaller gas disk radii closer to the ONC. So again, I think at least in the ONC there is a very strong argument for external photoevaporation. Also, I think it's interesting to look at the poster by Megan Ansel on Lambda Ori, because this is another massive star-forming region, but it's older, more comparable in age to upper SCO, and you will see there that that population is not very different from upper SCO. So this is perhaps telling us that planet formation is more important on a longer time scale, and this is what we see. I don't know yet, but I think it's interesting to look at those results as well in relation to what we have been discussing here. Now, let's go into the surveys where it was possible to precisely characterize stellar masses thanks to additional effort that was put in for those regions. So this is an example of the results that we presented for the chameleon star-forming region. On the y-axis, dust disk masses, x-axis, stellar mass. And what you see from this type of plot is, first of all, a large scatter. At any stellar mass, there is a large range in dust disk masses, or again, millimeter flux densities. But on top of that scatter, going back to my first point in the presentation, there are clear relationships. And so there is a clear, steep at this age relation between dust disk mass and stellar mass. In relation to the low mass stars, I really want to point out a few interesting talks in this conference that look at better characterize the dust disk properties for these objects, as well as the gas content, which I think, as I will mention also later, is really a key thing here to learn more about disk evolution. In relation to the dust, what we have learned when we put together different star-forming regions is that this relationship between dust disk mass and stellar mass steepens with age. And you can see it very clearly now when you go towards the upper SCO region. So what is driving this relationship? So I was very happy to contribute to this paper led by Paola Pinilla when she looked at the possible effect of traps in population of disks where grains are growing and also drifting inward. So again, y-axis dust disk mass, x-axis stellar mass, all these different lines are best fit relation to these quantities in different star-forming regions. And here you can see in red the population of disks that she considered at 1 million years, so very early on, and then their evolution at 5 million years. And what you notice by looking at these different panels is that only if you have strong traps for relatively massive stars, so solar mass or higher, then you can reproduce the steepening. Otherwise, you are going to lose your grains. So perhaps this is related to the type of planets that you can form in, but in any way, I think it's an interesting point to consider when putting together results from these different surveys. Now, a question that has been asked quite a bit in the literature: how do the dust disk masses compare to the mass in solids in planetary systems? So again, for reference, we have the dust disk mass, stellar mass plot for chameleon now, without upper limits, just for clarity. And then we have the, I overplotted here the D-sharp ring sources where the dust disk masses were estimated independently by Case Doulemont. And you see what you expect. These objects are not outliers, but they are on the upper part of the distribution of this disk population. So that's something to keep in mind when discussing this type of disks. You can also do the exercise of putting together, summing up the solids that we have in the planets in the solar system, and that's where the solar system would be placed in this diagram. And you can do the same exercise for the TRAPPIST-1, and that's where the TRAPPIST-1 would be located. Bear in mind that this is a log scale, so some of the uncertainties that we have in the solar system core, cores of the giants are not that relevant here. But then you want to ask, what is the typical behavior? So what is the typical mass in the Kepler and RV exoplanets, and how this is comparing with the mass in solids? And there were already a number of papers out there to discuss this comparison, but I want to highlight, I want to take my time to highlight some of the biases that needs to be taken into account when doing this comparison. And to do that, I want to use the graphics that Heismulder is using in a paper that has been just submitted. So what you see in this plot is a cumulative distribution as a function of planet mass for different surveys. In particular, if you look at the exoplanet.eu, which basically collects all the planets that have been detected, you would infer this pink, light pink curve. But you need to keep in mind that that type of catalog is biased toward giant planets because they are easier to detect. Instead, if you would take a volume-limited survey, radial velocity in this case survey, like the Mayor and collaborators, your cumulative distribution would be lower, skewed towards the lower mass planets. Then you need to take into account the occurrence rates in these surveys, the fact that giant planets are actually not very common, as we heard by Didier Queloz early on, while the lower mass planets are more common. And if you do that, then this is the intrinsic, de-biased, if you want, cumulative distribution. For disks, there is an opposite problem. As I mentioned early on, we are biased towards disks around low mass and dwarfs. So you need to take that into account if you compare with exoplanets. And now, if you calculate the cumulative distribution for stars that are more similar to the ones detected toward covered by exoplanet surveys, then you would see that the cumulative distribution is biased in the other way. So if you put everything together, you consider these biases as well as the fraction of stars that have disks in this system, then these are the cumulative curves that you are going to get. And they are very similar. In particular, the average mass in solid is the same in the radial velocity, Kepler, and ALMA surveys. So this is not to say that these disks are not forming planets, but it's just to say that it is not the disk mass available in class 2 system is not a strong argument against planets have formed in these disks. The problem remains, however, for low mass stars, because as it was shown in other papers, the behavior of dust disk mass as a function of stellar mass is decreasing, but in terms of solids, the amount of solids is increasing towards the low mass stars. So this is suggesting somehow a redistribution of the mass from the outer to the inner disk. And I really want to encourage you to see the talk by Nienke van der Mare, because she goes a step forward in collaboration with Heismulder. They look at disk morphology and exoplanet occurrence as a function of stellar mass, and they try to place together our understanding of giant planet formation and lower mass lower mass planets in the context of disk morphology. So a very interesting result, I think. Now let's move on into sizes of disks. So what do we know? So this is a plot that summarizes the most recent homogeneous analysis of dust disk sizes as a function of millimeter luminosities for different star-forming regions, and they are ordered in terms of age from the young to the old. This R68 is the dust radius that contains about 68% of the millimeter flux, and the modeling has been done self-consistently by fitting visibility data. And when you look at this plot, you see some of the results that were presented already in other smaller surveys. So the first one is that dust disk sizes are correlated with the millimeter luminosity, and also disks in the older region upper score are smaller than in the younger region, again because they are less luminous. However, something a bit new here is that these relationships, they are not strictly, the power law index is not strictly 0.5, so there seems to be a diversity there as well. I encourage you to see also the talk by Zornpass, because he uses this population synthesis model and connecting also to the possible presence of planets to explain some of these relationships. Now, the figure that I presented to you before was done looking only at one wavelength. And you might wonder, what is happening if I observe my disk at different ALMA wavelengths? And so the paper of Tazzari, which just came out, is actually addressing that question. So here is an example of the 26 sources that, where they have 3 different wavelengths. On the upper panel, you see the visibility data with the dots and the best fit with lines. And in the lower panel, these empty circles are actually the R68 for the 3 different wavelengths. And you can see that they are rather similar. And in fact, if you look at the entire survey, so here you have the R68 at 1 wavelength divided by the R68 at 1 millimeter, you can see that there is not much difference. And the main result from this analysis is that the 1.3 and 0.9 millimeter disk sizes are basically the same. The disks at 3 millimeter are only 9% smaller than those at 1 millimeter, which tells us that these large grains are present throughout the disk, and perhaps there is not much drift there. In relation to that point, although this is not a survey, I would like to highlight this plot by Fenlong's paper, which is also a very recent paper, because it also shows what is the morphology of disks at 2 different wavelengths. And it tells us, again, that in these disks where there are structures, dust trapping seems to dominate. And you can see, in fact, a very similar morphology as these different wavelengths. So this is something to keep in mind when we want to use techniques to calculate the dust disk, the total disk mass based on wavelengths, multiple wavelengths, millimeter observations. Now, let's move into the comparison of between gas and dust disk radii. So this is a nice work by Megan Ansell in 2018, looking at the lupus disks, gas radius on the y-axis, dust radius on the x-axis, and this is a one-to-one line. So disks are in the gas appear larger. Now, Sanchez has expanded the analysis in a paper that has been submitted and received actually a positive referee report. And so here you can see many more such disks. And what is important now that there are many more disks is that you can get an idea of the average or the median CO radius over the dust disk radius. And this is almost 3, which is telling us that it's not only an effect of optical depth that the gas is more extended. There is these disks have undergone grain growth, radial drift up to the first strap, and this is most likely what determines their disk, dust disk outer radius. Now, gas disk masses, this will be very short because there is another talk about that, but I want to make a few points. So if you felt that it was difficult to measure dust disk masses, so you need to buckle up for the gas disk masses, because this is even more challenging. So the challenge here is that, first of all, you have to find a molecule that is abundant, and therefore most of the surveys have gone towards trying to detect the CO, because it's the second most abundant molecule after H2. And you also need to find lines that are optically thin. So most of the surveys have gone searching for 13CO and C18O transitions. But there are all sorts of, keep in mind that these isotopologues are not very abundant, but there are also other problems, and that is that we don't quite know what is the H2 over CO ratio in terms of abundance. Is it similar to the ISM? Most likely not. So we don't know. And then there are further complications related optical depth I mentioned, but also the gas temperature, CO freeze out, isotope selective dissociation. So I'm very happy to leave this hot potato really to the next speaker. Just to briefly summarize what has been found, here are two plots from the early surveys, the lupus and the chameleon. And when getting this data, the surprise was really that there were few detections. And so the CO isotopolog lines were faint. And there is a huge discussion in the literature on whether this is because the gas mass is low or the CO abundance is low. There is a nice paper by Bergen and Williams going through some of these aspects. It seems like the community is converging towards the low CO abundance. But I also want to point out, also to steer a bit of the conversation, some papers that did not quite need the CO low abundance. So for instance, in the case of TW Hydra, that doesn't seem to be needed. And there are also a number of objects in the Diana project, in the paper by Voigtke, where the depletion of elements is not really needed. I know also of a paper that is in preparation, and I was told that it will be submitted this week. So hopefully the results will be out soon. And so what you can see here is the C18O line as a function of dust disk mass. And here are the objects in black in lupus and the one in chameleon where the C18O was detected. And you can see here with different lines, different type of models. And the one that seems to fit rather well is the dark blue one, which actually does not require any depletion. So again, this is more to steer the conversation than to tell you that I have an answer. I don't have it. Now, you can also use the surveys to learn a bit about disk evolution, and this has been done. So let me report the results. As we heard in the previous talk, this is the question of how disks evolve is actually a very important and yet unanswered question. So whether the evolution is driven mostly by viscosity or by MHD disk winds remains unclear. There are posters in this session testing accretion models by Colmenares and Diaz, and I encourage you to see them, looking also at permitted emission lines. And I also want to highlight the presentation by Emma Whelan, because she actually has the first detection in spectrostrometry on an MHD wind in the oxygen 1 low velocity component. So this is very, very interesting. Now, back to our surveys. The zeros order prediction for viscously evolving disks is that gas disk masses and mass accretion rates are correlated. And I underlined here gas, okay? Carlo Manara was the first using these surveys and showing us what is available in terms of mass accretion rate and disk masses. So you can see here on the left panel, the comparison with the gas. And again, unfortunately, it's full of upper limits. And so this turns out not to be very useful. However, on the dust side, there was an identification of a positive correlation. So the question that arises is, does the correlation between the dust disk mass and the mass accretion rate prove that disks are viscously evolving? And I'm afraid it turned out that the answer is no, it doesn't prove it. And these two papers independently looked at this problem. And they found out that in addition to looking for the correlation, you need to take into account the spread of these measurements, which unfortunately is large for these regions, as you can see in the plots. So the scatter...
Ilaria, you have five more minutes.
Thank you. So the scatter in mass accretion rate, dust disk mass can be reproduced if the viscous time scale is as long as the age of this region. And you may think it's okay because these are chameleon and lupus, but it's not okay anymore when you look at something like upper SCO. And this is a recent paper by Manara showing that the scatter is still large. So all these results, however, hinge on an important assumption which we should keep in mind. And this is if the dust disk mass is a good proxy for the total disk mass, which I have to tell you, I'm not sure anymore, especially when we look at all the regions. Finally, on this dispersal, I want to point out this nice paper by Lovell, where they look now at dust disk masses versus stellar mass, but including class 3 sources in lupus. And what you can see here is the gap in the dust disk mass between class 2 and class 3 suggests a quick dispersal. But again, keep in mind that here we are only looking at the dispersal of the millimeter grain. So it's not clear whether this is related to photoevaporation, for instance, or planetesimal formation. And again, I encourage you to see this talk by Michel, where he looks also at the connection with debris disks. Now, I have very little time, so very quickly on longer wavelengths. There is actually a nice talk by Cotens on the VLA centimeter survey of Ophiuchus A, and highlighting already some things you could do with the NGVLA. So the most obvious things, I think, and also very exciting, is dust disk masses. You could actually resolve the problem of the optical depth that we have been discussing before. Dust trapping, this is a nice simulation by Nienke van der Marel, is in the NGVLA book, and you can see how at different wavelengths you will be able to test some theoretical predictions. And also another things that we pointed out in the NGVLA book, this is in 2018, that you can do imaging of disk wind by looking at the centimeter free emission, as Barbara actually mentioned in her talk. I wasn't aware of those results, but very interesting ones. So in conclusion, I think, and it was nice to review really, that the surveys have, with ALMA have really delivered what are the typical disk properties, their spread. What have we learned? We have learned that the spread is large, but we shouldn't be worried about it. We should be happy, actually, because there is a large spread also in the outcome of planet formation. So we are witnessing the spread early on. In spite of the spread, there are clear trends that we should pay attention to in relation to stellar mass, environment, age, and I'm sure there will be many more once we dig into these and other data sets. And also, I think we need to keep in mind, again, that when we look at the continuum emission, there is the effect of some type of planet formation into it. And for the future, at least, I would like to see a similar large effort on the gas content, better characterizing the gas masses, the gas radii, and learn how they evolve with time. Thank you.
Thank you very much, Ilaria. Again, this was a whole lot of information. And there are quite some questions about this. So, for example, when we come back to the story you had about linking the mass in the planets with the mass in the disk, there's a question by Laura Fleck, who asks, why do we link the mass in planets, where we know most of it is in gas, with the solids in the disk, as opposed to using the total disk mass?
Oh, I'm sorry, I did not make that clarification. So when we look, oops, I have to go back to my slide, I'm sorry. Here we go. Okay. Screen. So I should have made that clear. So these plots are made considering the mass in solids in exoplanets. So we are not looking at the gas. So we are comparing apples with apples, or in this case, solids with solids, right? So we are not looking at the gas.
Thanks. There was another question which may ask some clarification by Jake Simon. and that was when you talked about the M dust versus M star correlation, and that it actually steepens.
Yeah.
And the only way to explain that was with very strong traps as opposed to weak traps. So can you maybe clarify what you mean by a strong trap and a weak trap?
So I don't have the slide to show you that, but basically it's strong in terms, obviously, of the density, the gas density that you see. And it is, I think Paula would be best to answer this question, so maybe we can move it to the other session. But it's a strong trap would be the one in which you accumulate more of the millimeter grains, and so you wouldn't let them flow through your trap, basically. And this is the one that would be generated by a more massive planet.
And why does that cause the steepening then? Why does it...
Yeah, oh, sorry. Yes, so the point is that only if you have these strong traps, you can actually keep the millimeter grains out in the disks around more massive stars. Otherwise, you see that they filter through somehow.
Okay.
That is the point.
Okay, thank you. Then we had a question asked by Daniel Price, and this is about the correlation of disk mass with stellar density. Is there something like that?
We have not looked into that. I think that's a very interesting question for the more massive star-forming regions. I would imagine it shows a similar, you might find some similar behaviors with, like for the ONC, because most of the stars would be closer to the center, and then probably there are the more massive stars, and so you would see the effect of photoevaporation again, external photoevaporation, I would think, but nobody, as far as I know, has looked into that aspect, which I think is interesting. Yeah, thanks.
Okay. Then there was one other question, again, coming back to this millimeter emission and whether it's optically thin or thick. And so are we certain that the millimeter emission is optically thin? And can we test that on a subsample of disks, for example?
Yeah, no, I want to make clear that I don't think it's fully optically thin. In fact, as I mentioned, there are already 2 studies showing that there is some optical depth that needs to be taken into account. Now, a factor of 3 difference is not a huge effect for astronomers. It is not for me. I'm happy with that. Yeah, we need to take that into account. And testing, absolutely, I think we should. And I think that's why going at longer wavelengths would be very valuable. If we could do many a survey with the NGVLA of some of these star-forming regions, I think it would be extremely valuable. Yeah.
Okay. And then there was a question by Lukas Tichonek. Given that planet formation efficiency is of the order of 10%, doesn't that imply we still need to form planets earlier than class 2?
I'm not sure I understand planet formation efficiency 10% based on, so the giant planets are rare, right? So they are only 10%, but I would say that actually planet formation is very efficient based on the mini Neptune and super Earth that have been detected. They made up, I mean, 80% of the stars have those. So I would say wherever you look around the star, you ought to be find some planets.
I think it maybe it comes back.
Oh, I'm losing you.
I think this question probably comes back to the relation you showed between the mass in the solids in the exoplanets and the disk mass, and that there was enough mass to make all those planets. If you look at the disk mass in class 2, but we know that in class 1, the disks they are way more massive. So do we still need to make those planets early, or can we now, are we happy with making them in the class 2 phase?
Okay. So the point of that slide again is not too much to say that planet formation can happen late. It's just to say that those data should not be used to make the claim, right? So I think I'm perfectly happy to form planets early on. I have no problem with that. I just think the amount of mass in class 2 source is not a strong argument for saying that planets have to form earlier. That's my only point.
Okay, and since we are talking about the earlier object, there's a question that asks, which effect do you expect to be responsible for the difference in disk size around younger disks? For example, the size of class 01 disks in Perseus and Orion from Tobin 2020.
Okay, I might have missed that, so I apologize for it. My understanding is that it is extremely challenging to measure the gas disk size at early ages because of the envelope. So distinguishing the disk from the envelope is very difficult. That said, I think it should be done, and I think an excellent test of disk evolution would be to look at disk sizes as a function of time. I think that would be very nice. If I can say, I think we should be doing also upper score with ALMA in terms of determining the gas disk sizes, because it's important at 10 million years to have that anchor point, as well as looking at the young ones. Although I think if we look at the old ones, we won't have those problems of, we don't have the problem with the envelope, and we need to go down in sensitivity. That's the main issue there. So in relation of what we would be learning, we would be learning about viscous evolution. And so that's clearly very important, because it would be, if really the gas disk sizes are growing, then we are going to learn that disks are viscously spreading, which is key to our understanding of evolution. So,
yeah. Okay. Correlation between the disk spectral index and the disk age.
I'm afraid I lost you at the beginning. So can you repeat the question?
Is there a correlation between the disk spectral index and the disk age?
I have, so at millimeter wavelengths, the spectral index millimeter wave.
Yeah, I suspect they mean the alpha. Yeah.
Okay, the alpha. Okay, so I'm aware of this paper by Marco Tazzari, let me see, where they have looked at Ophiuchus. Let me see if I can find it. Yeah. And between Ophiuchus, Taurus, and Lupus, there doesn't seem to be a difference, okay? But they are also pretty similar in age. So I think it would be worth doing some older region and testing that hypothesis that you made, whether they are different. I mean, that would be related to grain growth. So it would be an interesting point to look at. Yeah. I'm sorry, Inga. I missed a part of the. Yeah.
Larger dust masses can be underestimated by a larger factor than low dust masses, just because of the optically thin assumption. How does the relation m dust versus m star squared change because of this?
Nobody has looked into that, but you can imagine that it will become even steeper, right?
Okay.
Yeah, I think it would be important. And, the other point I made here, so nobody has actually looked into including now the dust disk sizes into the equation of calculating dust disk masses, right? we have seen that the temperature of the grains depend on the outer disk radius, so why not to have a more consistent approach and including that extra information to calculate dust disk mass as a function of stellar mass.
Yeah, I think what you showed, the dust masses that came out of the SED fitting, of course, to some extent, they do take this into account because they do actually have a dust temperature calculation inside it.
Yeah, that is actually correct. And I think I have the slide here. I'm only showing one plot from Ballering and Eisner, but they have another one in which they did not, in one they take into account the dust disk size and in the other not. And yeah, they have more precise dust disk masses, of course, when they take into account the dust disk radius. Yeah, but this was done only for torus now, yeah, where we don't have sensitivity yet to the lowest mass stars. Yeah.
Okay, I see here also a question by Gijs Mullers. Will it be possible to look at correlation with stellar ages, not by star-forming region, but by the individual stellar properties, for example, with the new Gaia data?
Yeah, the problem, I think, is that when we determine ages, we have to rely on evolutionary models. And I'm not too confident of individual ages. I'm not an expert on that, but I remember a very nice discussion of this topic in a previous Protostars and Planets conference. And my understanding was that the ages that we from clusters are better determined because you look at the ranges, and it's a bit dangerous instead to look at just one age. And so it's more the evolutionary models than the fact that now we know the distances.
Okay. And maybe a question that aims more at the future. What are the interesting regions you want to observe with an ALMA survey in the future?
Me? Upper scope, gas radii.
I suppose the question is towards you. Or yeah, the community as a whole.
I think that would be very important. I mean, as you see here, I was myself very pleased to see this table. I mean, frankly, there has been a lot done in terms of surveys. Again, high mass, low mass, different ages. So I think there was quite a lot done, but mostly on the dust. And I think we need to move forward and think about the gas as well. Another thing that I think would be very valuable are deep gas observations, especially C18O. I know it's faint, but if it is true that it is a good tracer for the gas disk mass, I think it is worth investing the time. That's my opinion.
I think it's very important to repeat some of these surveys with very deep gas observations. I absolutely agree. But I also think it might be very interesting to repeat them with higher spatial resolution.
I would love to have high spatial resolution for each of these disks, but I'm afraid it won't be possible. But I think selecting some particular regions in this, for instance, disk mass, stellar mass diagram to make sure that we cover roughly the region at high spatial resolution as well. I think that would be very nice. Yeah.
And I think we only have 20 seconds left. So I suppose we leave it here. Thanks a lot for answering all those questions. The remainder of the questions will be taken over to Slack, I suppose. So thanks again for a very informative talk, a very nice summary. And I think we are heading now into a break, unless we have some special announcements from our organizers.
No, that's it. Let's come back in 30 minutes. We're going to leave you with a not disk related poll for the break. And see you back in 30 minutes. Okay, it's time. Before we start, let's look at the results. Well, Python is not a surprise, I'd say, but the 40% of people using, does that mean that we have 40% of modelers in the audience? I've seen some discussion on Slack already, so I'm just gonna mention briefly, remember that there is a code of conduct because these things can end up in war. I think that's it. Inga, you can continue.
Yes, thanks a lot. I also think this is a very interesting poll, and I'm happy I'm not completely outdated because I'm using Fortran as well. So apparently it's still popular. So let's move on. We have the third review talk of today, which is by Anna Miotello from the European Southern Observatory in Munich, and she will talk about disk chemistry.
Okay, hi everyone. Can you hear me well?
Yes, we can.
Okay, so I'll try to share my presentation now. Can you see it?
Yes, but it's not.
No,
I mean, we yes,
Oh.
we see the presenter view. We see all the little slides and the next slide. So this is not the display view.
Okay.
And if you click on the no, if you go to that mode and then click on the top left, there's two arrows.
Yes. Okay. So now you see it correctly.
Perfect.
Yes.
Yeah. Sorry for the little inconvenience. So thanks a lot, Inga. Thanks a lot, the organizer, for having me here today to talk to you about this chemistry and for giving me this impossible task of reviewing the chemistry in disks in 45 minutes. So for this reason, I've decided to take a little angle. And what I will be focusing on today is mostly what has been the contribution of ALMA in this chemistry, and in particular in the past few years, a bit, not exactly after HL Tau, but kind of in this time regime. And the other thing is that, as usual, I have this word in my title, chemistry, that is scaring a lot of people away. At least this was the effect that this word had on me when I came from my physics background. But then what made me change my mind was seeing this kind of observation. So here you see our beloved TW Hydra in sub-millimeter continuum emission and CO emission. So what you see is that, at least when it comes to sub-millimeter wavelength, the dust component, which is basically only, we think it's 1% of the bulk material that we have in disk, is not tracing the same regions that are showing up in CO. And the second thing is that even if you're just observing CO, actually you need to know a little bit of chemistry to really be sure that you're interpreting what you're seeing correctly. So the first reason why I think chemistry is really important for disks is that the chemical structure is tightly linked to the physical structure of disks. So observing, for example, molecular emission, you can get information about, for example, temperature or density in disks. The second thing is that we have now seen structures in disks. We have even seen protoplanets in the case of PDS-70, I'm sure that Andrea Zella will talk about this disk in the coming days. So now, if you're able to study the emission of molecules vertically and radially into disks, you are in principle able to understand what kind of material is available to planets who are forming at this location in the disk. And finally, what we know is that molecules survive in two different flavors. In this, you have both gas and you have solids, ices. You studying these components and disks also tell you what kind of material will be incorporated into the cores of planets and in the atmospheres. So let's exactly start from the icy component, and let's start from the snow lines. And let's try to understand why they are so interesting and important for planet formation. So what you have here is a nice cartoon from a recent review by Karin and Ted, who made this beautiful sketch, which I'm going to use throughout the talk. What you see here is the gas disk temperature. And you see that there are some lines, so there are some surfaces that tell you where different molecules freeze out. So you would have that at a higher temperature than CO, water will freeze out. So, and then as you go outer in this with the temperature even lower, around 20 Kelvin, that even CO can freeze onto the grains that are underneath it. So what we know since a long time actually is that the surface density of the disk of the solids increase right outside the snow line. So having information on their location is actually very important. Also, as you can see from this sketch, the properties of the material changes across the snow lines. So, for example, you see that in the very inner disk you will have bare grains, and then as soon as you cross the water snow line, you have grains that are coated with the water ice, and then as you go even farther, then you will have them coated with the water and CO ice. And this makes the grains stickier and stickier, and then growing them into larger pebbles will become more easy. And finally, the snow lines can also enhance locally the pressure in this, and this is very well linked to the dust traps that we know very well. So let's focus a little bit on the water snow line. And the water snow line seems to have very big implications for plant formation, because it has been shown by theory works and also experiments that the velocity at which grain collides and fragment is up to 1 order of magnitude higher if you have water ice coated grains. So what Andrea Banzatti et al. Predicted in their work in 2015 was that you could get information about the location of the water snow line looking at the spectral index. So we know that if we are in the optically thin regime and in the radiance regime, the spectral index of our continuum emission subliminal wavelength will tell you something about the size of the grains, but also the composition. So the opacity is linked to this spectral index. So what has been shown observationally is that when you can resolve the spectral index, you'll have that this diminishes as you go toward smaller radii. So as soon as the grains become larger, then the spectral index becomes smaller. But then if you reach the location of the snow line and your grains become bare, so you would have kind of a jump in the spectral index, and this could be observed. They call it a break in the dust size. On the other hand, the temperature, so the location of the snow line is expected to be at very small radii, so at 1 or few AUs, so very difficult to observe. So the first case in which, so the one case in which this water snow line was detected using this technique was the year later by Lucas Sies and collaborator. They observed this star V883 Ori, which was undergoing an outburst. It means that the disk would become much warmer, and then you would move the location of the water snow line at larger radii. At this point, the location would be resolved without observation, and this was the continuum map that they got for this object, where they could see this boundary region at around 42 AU. And when modeling this emission, they found that this sharp break was found at a temperature of around 100 Kelvin, which is consistent with the water snow line. Actually, it was so while I was preparing this talk, a paper came out, and it was on the observation of HCO plus in the same object by Lemker and collaborators. And they used HCO plus, which is a molecule that we know could be a tracer of the location of the water snow line. Just because you have this simple reaction, you see that as soon as you have water, then you transform HCO plus into CO and H3O plus. So when water is instead on the grains, HCO plus can survive. And you see here in the top plot, the emission of the HCO plus peaking at a radius of around 100 AU. And it's interesting because the authors also have detection of methanol in the inner parts of the disk. So you can also claim that this decrease of the HCO plus emission at the smaller radii, it doesn't depend on the optical depth of the continuum. So it's interesting because while doing this model, they found a different location of this null line, which is in contrast with this old work of CSI and collaborators. So I think this is a place where things are not settled yet, but we are lucky enough that Margot is actually presenting this work at this conference. So I'll invite you to follow her talk. And also, if you're interested in Waters null lines, I've seen another posterior contribution by Shatanotsu, which could be relevant. So, so what we have seen is that Waters null lines are in principle important for planet formation because of the stickiness of the grains. But on the other hand, these null lines are very difficult to observe because they are usually very close in, unless you have this kind of bursts. So what about ice lines of other molecules? Are these so important for planet formation? So from an observational point of view, what we have is this work by Jane Huang in 2018, where she has compared the location of the substructures or these rings and gaps seen in the D-sharp disks with the model temperature of the midplane. So you see here in these panels. And what she finds is that there is no clear link between the location of these structures seen in the continuum and the model location of the snow lines of different molecules. And a similar result was found also in the disks in the tower star forming region by Feng Long in 2018. And in this plot, you see the radius at which you find the gaps in these disks. And you see different disks with different symbol. And then as a function of the luminosity of the star, and then you see these colored shaded regions, which are the regions in which you expect the snow lines of different molecules to be. And she also doesn't find a clear correlation between the two. So apparently it seems like you could explain substructure, so probably the location where planets are forming with the location of snow lines. There is so there's a work in 2016 by Fayol and collaborators where they show that snow lines may appear at different temperature because the sublimation temperature can change with ice composition and morphology. So there might be a complication here. But so let's see other ways in which one could get the CO null line. I would say the preferred molecule is N2H+. And this is because you can form N2H plus by photon transfer. So you need some N2 in your disk, which will react with H3 plus to create N2H+. The caveat is that if CO is present in the gas phase, this will react with H3 plus much more efficiently than N2H plus and would impede the formation of N2H plus. And there is also another reaction, so N2H plus would also react with CO and get destructed. So, but this is good because it means that if CO is in the gas, you don't expect to see N2H plus. As soon as you see N2H plus being bright, it means that CO is frozen out. But you still need to have some N2 in the gas. So you would have N2H plus being bright between in a sweet spot where CO is frozen out and N2 is not frozen out yet. Okay, and this is exactly what I just said. Okay, so I would say that a very nice work that was done in order to understand the robustness of these molecules as CO's null line is this work by Mara Van Toff in 2017. And here you see some models that she has run using physical chemical models. So if you look at the plot on the right, you see exactly what I was talking about. So you have your radius. At some point, you have this finger of emission in H2H+, which is basically limited on the top by the CO snow surface and on the bottom by the N2 snow surface. But then what she found was that if you change the abundances of CO compared to N2, then you start creating this large region that you see at higher scale heights, which is due to the fact that there is a small difference in the photodissociation rates of the two molecules. So this has to be taken into account, and if you do that and you try to plot the location of the CO lines in models by changing the abundances, you see that the location varies. So N2H plus can be used as a CO line tracer, but some knowledge about this abundance ratio has to be there, and also on the disk physical structure. So keeping this in mind, there has been recently much more observation-based work by Cialici and collaborators in 2019, where he presents N2H plus observations of different very well-studied disks. So here you have the continuum emission on the top, then the N2H plus moment zero maps, and on the bottom the spectral lines. So what you see, if you plot the radial profile of these lines together with the continuum radial profile, what you see is that you can divide this set of sources into types of disks. The left disks show a bright, narrow ring, more or less where the continuum ring is, and then a tenuous extended emission in N2H plus. The second subsample of disk shows instead a broad torus which is extending across the dust disk. It's just outside of the dust emission. And the way the authors describe, so try to understand this behavior, is by modeling two types of disks. So you would have on the top here a flared, a much more puffed up irradiated disk, and on the bottom, a much thinner disk. So in the first case, you would have this region around 50 AU, where you have this vertically isothermal region, which is predominant. And then this finger between the CO surface and the N2 surface is so tiny. So you would have indeed that this region around 50 AU is what is really causing this steep emission, and then you have the broad component by the extended finger. Then instead, if you go to flatter disk, the vertically isothermal region is much less important, while the finger between the CO surface and N2 surface would contribute on the emission. You have the behavior that you see on the right. So in the first case, you can locate the CO and N2 line, and in the lower case, you can also place some upper limits on the location of the CO line. But doing some modeling, the authors find that the temperature that they obtain is consistent with CO and N2 being freeze out on moderately water-rich ice grains. Finally, another molecule that was proposed as a possible CO line tracer is H2CO, the formaldehyde. On the other hand, we know that this molecule could form through two paths. So one is on the grains and one is in the gas. So if H2CO was formed on the grain surface, then you could use it as a tracer of the CO line. But already in 2015, Ryan Loomis showed that when you start combining the two formation paths, then the things become more complicated. And in 2017, Karin had observations of TW hydra into transition of this molecule that showed evidence of the gas phase H2CO formation being important. And this finding has been now confirmed very recently by Jeroen Terwiescha van Scheltinga and collaborators in 2020. And now I want to win the prize for the person who pronounced the longest name in the whole conference. But apart from that, this work is a very nice work where Jeroen and collaborators have modeled orthospin and paraspin isomer transitions of this molecule. And they have shown that a gas phase formation is responsible for the observed gaseous H2CO across the entire TW hydra disk. So there might be a larger reservoir of this molecule, maybe in the ices, but what you see in the gas is formed through gas phase reaction. So probably this is not a molecule that you would use as a CO line tracer, but it's still very important because it's a prebiotic molecule, and it's probably the only prebiotic molecule that we are able to observe in class 2 disks. And here, just to want to show you something very new and very preliminary. So the detection of formaldehyde that we have seen so far in disks has happened in the very large and bright disks, but we have recently got observation and detection of this molecule in a few disks around binary stars, and these disks are much smaller and fainter. So it would be interesting. So something that we are trying to do with Michael Alba, who is the undergraduate student who's working with Stefano Pacchini and myself on this project, is to try and compare the emission that we see in these disks with the ones that are present in the literature and see what are the implications, for example, for prebiotic chemistry also in these environments. So stay tuned for that. So let's have a recap. So let's break for a bit and see what we have learned on snow lines. So we have seen that the water snow line is very relevant for planet formation because it allows dust growth. But on the other hand, the detection of this snow line is really complicated because in typical conditions, it is found at very small radii. On the other hand, you have ice lines of different molecules that are not so, for which we don't have such clear link between their location and the location of the substructures. But these molecules are much more easily observed by ALMA and can be used as ice line tracers. Another interesting implication is also that by modeling these molecules, you also get information on the disk temperature and ice composition. So this is really interesting. If you're interested in getting temperature on disks and on younger disks, then I would suggest you to go and see the talk by Mary van Toff, who's shown that younger disks can be actually much warmer. There are also a few caveats on this story on snow lines, because what we know is that actually disks are dynamical. So there are dynamical processes that can complicate the scenario. So for instance, you have the temperature and the surface density profile change with time, and this will also change the location of your snow lines. You also have grains, so grains and ices go together, and you have the sublimation and grain drift have very similar timescales. We know that there are diffusive flows, we know that there is pebble drift, and we know that there is possibly chemical evolution. So CO, for example, is very easily transformed into CO2 and CH3OH. So all these things can complicate this scenario. I won't go into much detail here, but there are at least 2 talks at this conference that try and tackle a few of these points. So please go and give a look there. All right, so now we move a bit from snow lines and ice lines, and we start talking about volatiles. So as we have seen, we can find in our disk, we can find an icy component, but the bulk of the material that we are observing in this is usually in the molecular layer. So we want to observe molecules when they are in their gaseous phase. And as I said at the beginning, this is interesting because their emission is strongly connected with 2 things, with the gas density and the gas temperature. For the temperature, we have already seen some examples with the snow line. Another ingredient that plays a role is also the abundances of different volatiles. And we'll see how these 3 factors play a role in the next slides. First of all, I would like to focus on the disk temperature and to give you only one example on one case where people have used the emission of a certain molecule to get information on the disk temperature. And this is the work by Salinas and collaborators in 2018. So they have observed this interesting morphology of the DCO plus emission. And what they have seen is that you would have this bright emission at smaller radii and then a second bump at larger radii. And they could reproduce the second bump by only considering the dependence on the temperature of the chemical reaction that would create this line. And this, I think, in this case in particular, this was due to a temperature inversion. that was expected when grains would decouple from the gas and drift inward. So I think this paper for me was very interesting because it showed how powerful chemistry can be to also constrain the physical properties of the disk. Then instead, if we shift a bit from temperature to gas density and therefore to the gas mass, the surface density distribution, and where you set your outer radius for your gaseous disk, then we start talking about CO. So CO is in principle not considered chemistry from many chemists, but actually you need to know a little bit of chemistry also for CO. So this is a molecule. The reason why it's supposedly not chemistry is because this is one of the simplest molecules that you have. You just have two reactions or two processes that limit the abundance of CO in the disk. So either you are very high up in the disk where you have strong far UV radiation and then CO gets photodissociated, or you are at very low temperatures, temperature lower than 20 Kelvin, and there CO is on the grains. For the rest of the cases, you expect CO to be there because it's very stable and also very bright. So if you want to detect it and you go and observe 12 CO, actually what you are doing is tracing the surface of the molecular layer. CO is so abundant that its lines at millimeter wavelength become optically thick, basically, at the surface of the molecular layer. So if you want instead to go and probe the column density, then you want to go to less abundant isotopology of the same molecule that would trace deeper down in the disk. For more massive disks, so very massive disks, there have been also observation of a much fainter isotopology, 13C17O by Alice Booth. But usually for, let's say, the normal disks that we have seen presented by Ilaria in the previous talk, C18O C18O emission should definitely be thin. So before going in the implication of these observations, there are two caveats that we need to take into account. So let's assume we indeed observe this isotopology, C18O in the disk. We have seen that photodissociation is the one reaction that you have. And this reaction is slightly different for different isotopology. And so we call it an isotope selective process. So this means that if you want to go from the mass of C18O to the mass of CO, and you just apply the isotope ratio between 18O and 16O that you would find in the ISM, you are actually wrong. But in between 2014 and 2016, we modeled this, and we think it's something that we can control with physical and chemical models that can deal with isotope selective processes together with freeze out. Then you have an additional step. So you want to go to the CO mass, to the H2 mass, and here is where things become more complicated because you need to know how much carbon is there compared with the H2 in disks. And as we will see, this is not so easy. So, but taking this in mind, you understand why also Ilaria was saying why people started carrying out a lot of surveys in all the different star-forming regions, targeting indeed continuum emission and CO emission. So the goal was to get the abundance, the masses, and the distribution of the dust and the gas simultaneously in the disk. And as she has already also mentioned, as Ilaria has mentioned in her talk, it was a big surprise to see that as soon as we got the data, this CO emission was really faint. So here I show this plot for the lupus star-forming region, but there is a similar plot for the chameleon one star-forming region by Feng Long in 2017. And what you see here, so on the top you see the dust masses for the disk as a function of, so for each disk increasing by dust mass. Then on the middle panel, what you see are the CO-based masses obtained using the physical chemical models that I was talking about. And it's already striking to see that you only have a handful of disks that are as massive as one Jupiter mass. And then if you take these values and you divide them and you want to get a CO-based gas-to-dust ratio, this is what you find. So that really a few disks have a gas-to-dust ratio of 100 as we find in the ISM. And actually, coming back to what Ilaria was saying, If we are even underestimating the dust mass by a factor of 3, this is even worse. So it was clear that this was a sign of disk evolution. So on one hand, this could have been physical evolution, so that gas is dissipated very quickly already at these young ages, so in lupus and in chameleon, like sarcoma regions. And this would mean that giant planet formation has to be very quick or rare. On the other hand, the other option would be that actually is the abundance of carbon that is smaller and therefore of CO, so that CO is faint, but the gas is still there. And this, and that indeed carbon is locked up somewhere else in icy bodies or in more complex molecules that are then frozen out and in the midplane. So I won't go too much into the details of these two options, but I list here all the a lot of interesting papers on both the chemical evolution of carbon into more complex species or into solids, and I'll try to show you how you can actually probe whether this second interpretation could be right. So let's take a step back. Actually, these surveys were not the first place where we saw that CO was faint. And as usual, we go back to our beloved TW Hydra. And this was the one disk that was observed at the time with Herschel in the HD emission. So HD is the less abundant isotope log of H2. So in principle, is a more direct tracer of the disk mass. And when compared with the SMA observation of C18O, one finds that the CO-based masses are 2 orders of magnitude lower than what you would get with HD. Then Melissa McClure also had a couple of other detection in other disks using Herschel data. And Leon Trapman made a very nice modeling of this emission, and Mikkel Kama recently published some lower limit. So using some upper limit on the HD detection in other disks, was able to set some lower limit on the disk masses from HD. And what is interesting to me is that on one hand, we see that in disks like the lupus disks, the chameleon disks, or TW Hydra, you have this problem with CO, but as soon as you go to Herbig disks, this is not such a big deal. So CO is still very bright. So temperature might play a big role in here. But so let's go on with this TW Hydra disk. So in 2015, Mikkel Kama tried to fit all together the lines that we had for TW Hydra from the CO isotopologues, the HD lines, O1, C1, and the hydrocarbons lines that were observed in 2015 by Kastner and collaborators. What was interesting was that C2H was actually quite bright compared with the CO. So you see it's basically as bright as some of the CO isotopologues lines. And the only way to fit all this together was to deplete carbon by 2 orders of magnitude, but then to deplete oxygen even more so that the C/O ratio would be larger than 1. And the same year then nicer observation of situation TW Hydra came out with published by TED and showed this beautiful ring emission. So what you see is that C2H is a very strong emission and CO is fainter than expected. So the way that this was interpreted is that you have indeed your surface of your disk where you have volatile carbon and oxygen. If these volatiles are locked up into the midplane, either through more complex molecules or solids, and if you have a preferential way of blocking oxygen rather than carbon, you will have a molecular layer where you are depleted in carbon and oxygen, so CO has less ingredients to make itself. So basically, CO would be less abundant, and the CO ratio would be larger than 1. This would mean that you would have some free carbons available that are not immediately bound to oxygen and able to start some new chemistry. And this would be the hydrocarbon chemistry, which is basically just adding some hydrogen to the carbon. And the easiest, simplest hydrocarbon molecule that you have is C2H. Another interesting thing is that C2H is very sensitive to UV. So as soon as you have some UV coming from your star, the emission is boosted. So in order to try and test whether these idea was correct, or at least was in line with what we were observing in the lupus discs. We obtained in 2000 in cycle 4, we obtained C2H observations in a few discs in lupus where we had different CO-based gas-to-dust ratio. So the idea was to see whether for those discs where you saw that the CO was very faint, you could get bright C2H as found in TW hydra. And this would support the idea indeed that, that this evolution that we were seeing was a chemical evolution. Here below, I list a bunch of other C2H observations, some pre-Halma observation and Halma observation of this molecule. In particular, there is a nice paper in 2019 by Jennifer Bernier, who published observation of C2H in 14 discs that span different ages and stellar luminosity and stellar masses. So I haven't, in this talk, I'm not focusing very much on younger disks, as the chemistry there can be very different, and maybe some of that will be covered in the talk on Friday. But if you're interested, this is a beautiful paper that one should go and look at. But so these were the observations. So you see the color map is the situation, then the contour is the continuum. And when you plot the integrated luminosity of this line as a function of the disk mass for the disk that we observed, this is what you find. So we compare this with the physical chemical models, and what you have is that, for example, if you go at a given disk mass, so at 10 to the minus 2, and you deplete your volatile abundances of carbon and oxygen by 2 orders of magnitude, you would get this orange dot, this completely out of your observation. But as soon as you start playing with the abundance of oxygen, so you deplete it more and more, you see that the model, so go from orange to green to blue. You have this jump as you go from the level of 1 to larger than 1. And you start getting into the region where we have these observations. So we interpreted this as a hint that indeed some chemical evolution is happening. And this is interesting because it was also found using different modeling works. So the one on the left, these are, and the one on the left, you have here column density of the modeled C2H emission for the ion loop disk. And you see that indeed, as soon as you move from a C over ratio of 1 to larger C over ratio, you have this jump that we also see. And also, I want also to mention this paper by Davide Fedele and Cecil Favre in 2020, where they make kind of a modeling paper where they see how different molecules vary if you change the abundances ratio. And you see that indeed, in order to get brighter C2H lines, you need to have C over ratio that are larger than 1. So you see these gray bars here. So I've seen that there are very interesting talk at this conference as well that focus both on a C2H emission, but also in general in determining the volatile abundances in disks. So I point you to these 2 talks here. Another interesting fact that that we found was that if you try to plot the C2H emission as a function of molecules like CN and HCN here, you see that there is a clear correlation. We know that CN and HCN are molecules that are very sensitive to the UV radiation. But another interesting thing was that when comparing C2H with CN for the discs and lupus, we saw that this correlation was steeper than 1. So it means that these 2 molecules have a similar chemical origin, but it might be the C2H is depending more strongly on something else. We know that CN doesn't depend much on the C over ratio, so the C over ratio might be the one that is making this correlation to be steeper. And now I want to use one slide to focus on sulfur-bearing species. So this is a very interesting topic because sulfur-bearing species are found to be quite faint in disks. So this is a very nice work by Dima Semenov and collaborators in 2018, where you see where they have studied EM tau with different sulfur-bearing species. And what you see is that basically only CS has been detected. And the story here seems quite similar to the one that I've just told you about carbon. So what they suggested that that sulfur is basically locked somewhere else, so maybe in larger species. And the other interesting thing is that when they try to get the CS over SO ratio and the CS over SO2 ratio, they seem to require a large C over O ratio. So this is again consistent with the hydrocarbon story. But another very interesting work that I want to highlight here is the study of the CS emission in TW Hydra by Richard Tick in 2018. And here Richard had basically 3 transitions of the same molecule, and using that with LTE and non-LTE modeling was able to constrain the turbulence, the temperature, and the sigma and the surface density profile of this molecule. It was even able to give a limit on the disk mass that was consistent with the one obtained with HD observation. So another interesting fact was also that the CS emission was extending to much larger radii than CO, for example. So this is telling us as a molecule SCS, which is indeed quite faint because of the lack of reactive sulfur in the gas phase, can actually tell us a lot about the physics of the disk. So now I'm changing again. So what I want to talk about now is another molecule that, in contrast with CO, was found to be quite bright in disk, and is a CN. Here I want to present you, so what you see on the top is the detection of CN always in TW Hydra, and you see this beautiful ring. And the question then Paolo Cazzoletti asked himself in 2019 was, are these rings something common in disks, and is this related with the the dust structure? And actually what he found was that no, yes, so rings are basically everywhere, but they don't depend on the dust, surface, so the dust structure. So you would find rings even when the disk is full in dust. And this is because you have kind of a peak in the abundance of CN in the outer regions and in the upper layers, which is due to the fact that that you can create NH by having nitrogen reacting with vibrationally excited H2 molecules, and this then brings to C+ reacting with NH and creating CN+, and from that you go to CN. So you have basically that H2, that CN is very so basically where you find CN, you have good information about the far UV field. And the other thing is that if you look at this abundance plot, what you have when you get the column density of CN as a function of radius, you really get these rings. So yeah, to summarize, rings are produced naturally and everywhere in protoplanetary disks, and there is a strong link between the far UV flux and the CN emission, which is not related to the dust structures. I've also seen that there is a MAPS talk by Charles Lowe, which is also showing new observation of CN in disks. So I would point you all to this talk. Another very recent paper on CN has been published recently by Richard Tick and Ryan Loomis, and who have used line stacking techniques on TW Hydra, and were able to detect 24 out of 30 hyperfine transition of these lines. And they were able to measure the excitation temperature. And this to me is very, very promising, because when looking at the excitation temperature, they saw that the CN emission layer seemed indeed compatible with the emission layer at quite high scale height, so at Z upon R larger than 0.2. So this is consistent with the Paolo Cazzoletti's work, But they also mentioned that it would be nicer to trace the emission layer directly using geometrical method. And this is where I would like to point you out to the work of Teresa Panecke, who's just recently started to work as a PhD student at LISO with myself, and has actually worked with Laura Perez for her master thesis. She has studied the Elias 27 disk in continuum and CO emission with Laura, and she's now moving to CN, so she's moving to more chemistry project. And here, what you see here is the moment one map of the CN in this quite complicated disk. You see some channel maps, and what she has done was to use the geometrical method by Christoph Pand to get the emission layers in the west and the east channels for this disk. And what I find interesting is that when you compare this, so this is very preliminary, so stay tuned for more advanced results. But what we seem to see is that the emission of CN is indeed coming from a very high emission layer, which seems to be at higher scale height than CO. But CN was also included in some of the survey. So we have these beautiful images of CN in very well studied disks like TW Hydra, and we also have some integrated, but also some maps of this emission in, let's say, disks that have been studied at lower resolution and lower sensitivity. And this was published by Sirfan Trevisha in 2019 for the lupus disk. And what he finds is that CN is detected in 38% of the sources, basically the same fraction as 13CO detection, but no correlation is found either with 13CO or continuum. For two of these disks, for which we have the brightest emission, I think, SIRC was also able to produce maps and radial profiles for the emission. And again, you find rings of CN, and you find that the peak radius is around 58. For the rest of the population, however, CN seems to be quite faint. And when you compare it with the models run by Paolo Calzoletti, for example, you see that only disks with critical radii smaller than 58, you could explain that. And this could be an observational evidence that gas disks in lupus could be small. So again, where chemistry can tell you something about the physical structure. And again, that you don't necessarily need substructure to get CN rings. So let's try and get some take-home on volatiles as well. So we have seen that carbon monoxide is very faint in many Titari disks in different Stockholm region. And we think that this is linked to the fact that we have some chemical or physical sequestering of volatile carbon and oxygen. We have seen that hydrocarbons are bright and do not correlate with CO or the dust emission, but they depend a lot on the CO-over ratio, which needs to be larger than 1, and that you need some UV field. These types of molecules are really interesting because allow us to get information on the CO-over ratio. And we know that this is something that is measured also in exoplanet atmosphere. So this would in principle give us the possibility to link this chemistry with the composition of our exoplanet atmospheres. We have looked at CN. We have seen that basically you find rings everywhere, and that the location and brightness of CN rings is linked again to the far UV flux. And that can give us some information on the disk scale height, as well as on the disk extent. And finally, CS seems to be, despite being quite faint, is a great tracer of the disk physics and chemistry in disk. As you may have seen, I haven't talked about complex molecules, and this is because it's hard to detect them in class 2 disks, while it's much more easy to detect them in class 0. And this is seen, for example, in the PIL survey and in other surveys, and maybe the talk on younger disks will cover this on Friday. And before closing, I would just like to show you a couple of slides on what is coming soon and what are the future perspectives in this field. So
your time is in principle up, so can you be very short?
Yeah, I'll be very short. So two things. Large programs coming. It's the FAUST, which is focusing on younger disk. And there is a talk on this by Eleonora Bianchi, and if you're interested in similar topics, you can look at Claudio Codella and Linda Podio talks. Something that I haven't talked much, but that everyone knows is coming very soon is the MAPS large program, which will show radial and vertical disk structure at 10 AU scales in 5 disks with substructure. But I know there are more than 5 papers coming out soon, also just judging at the numbers of talks at this conference. So please go and see all of them. I'm really curious about it. I'm really looking forward to the papers coming out, even though there are some other spatially resolved papers here. And finally, and I will stay with this slide as my thank you, I kind of echo what Ilaria was saying. So if you look at lupus, for example, IM lupus is the only one, for example, that will be covered by MAPS. And we do not have a chemical census of the bug population. With chemical census, I even mean CO. So we don't have deep CO observation of these disks, which actually build up the bulk of this population. So if you really want to make a link between the plants that you form, their chemistry and the chemistry of disk, I think we should push for that. And thanks a lot, and sorry for being late.
Thank you very much. This was a very nice talk, taking us on a huge tour along very, very many molecules. I see quite a number of questions, maybe less than for the dust actually, which is not surprising, but in any case. So there's a question about the water freeze out. Is the water freeze out that has been shown to be 150 Kelvin in V883 Ori case, is that actually reasonable to expect?
So let me go back to the slide that we're referring to. So this one probably, oops. So yeah, this one, the 100 Kelvin, this one, right?
Yeah, is it reasonable to expect a freeze out temperature of 150 Kelvin for this object, given the typical disk densities?
I am not sure of the detail of this particular object. I would say in general, this is a temperature that you would expect for a water snowline. But I'm pretty sure that more details on the modeling of this object are presented in the paper by Lemker, where they have actually modeled this more in detail. So I haven't, unfortunately, read the paper in details yet. So I would point you to this paper or to her talk to see more details.
Okay. So maybe staying on the snow lines, could you comment on the vertical structure of the snow line? The location depends on the scale height that you're probing, no?
Yes. Yes, so maybe going to this slide here. Yeah, so indeed, so we talk about snow lines, but actually these are snow surface. So this is telling us that a lot about the physical structure of the disk has to do with the CO snow line. So in this sense, taking so if you see a ring in a certain molecule, for example, in 2H+, so I think the message was a bit this one, so that if you see a ring or something, that it should be tracing a snow line, it's not given that this is exactly telling you the location. There might be some dependence both on the vertical structure, so as you have seen here, but also as Meryl Van Top was showing with your modeling, also on the abundance of the different molecules. So you can see here that the location of the CO snow line can change with the abundance. And in principle, what you would really need to do is to do a proper modeling of the source, both on the physical point of view and on the chemical point of view.
Okay, thank you. And then there's a question, or a few questions actually, related to this CO issue, that we're getting very low disk masses from CO. So one question posted says, since the continuum emission is mostly optically thick, could the continuum subtraction result in an over-subtraction of CO emission and thus lead to lower masses?
So in principle, I would say yes. The question is, are we really sure that most of the continuum emission is optically thick? This I'm not sure. So it's definitely true for very massive and bright disks, where, for example, HD 163296, we know that this is a problem, that you have that the inner regions, the emission is optically thick, and you see basically, you see then the effect on the CO detection. But then these disks are much smaller and much lighter, so I don't know how much of an effect this would be. Plus, in the survey, we have larger beams, so you have kind of a beam dilution. So yes, I think it would be worth looking into how much the CO emission, like the integrated CO flux, could be reduced by the effect of optical thickness in the continuum emission. But I wouldn't be able to give a number on how relevant this would be.
Okay, thank you. There's a related question again on the disk masses. So even if you use the CO isotopologues, don't we still miss the midplane where CO is frozen out, but where most of the disk mass is sitting?
Yes, so so this is actually considered. So when I show a plot like this, so the CO-based masses that I get from here come from a set of disk models that model both the freeze out and the photodissociation. It means that when I get a total disk mass in my model, I'm considering that I'm not seeing a part of the CO because it's frozen out. So the error bars that you see here in the disk mass are actually showing how the CO emission would change if you have different disk properties. So in my set of models, I have different scale heights, I have larger and smaller disks. So this is kind of taken into account in these error bars. In some cases, this can be quite big. But how CO freeze out is now implemented into physical chemical models seems to be quite trustable. So I wouldn't worry. So I don't think that this is where we should worry much for the CO-based masses.
Okay, thank you. Then we have a question here by Dima Semenov. Do we know about nitrogen depletion in disks other than in IM Lupi, the study of Ilse Cleaves from 2018?
Not that not on the top of my head, I might be wrong, but yes, and this is also something that, for example, I didn't manage to get in this talk, but this is definitely a good question that we should follow up. And then I don't know what we know now from the MAPS results, so there might be something back. Let's see.
Yeah, so let's have a look at the MAPS talks that are also online. And maybe one more question coming back to the carbon depletion that you suggested from a couple of papers. Is the amount of carbon sequestration that is needed to explain the low CO abundance consistent with the abundance of carbon in the solar minor?
With the abundance, sorry, you dropped. Is it consistent with the abundance of carbon?
Of the solar system, the carbon in the solar system minor objects.
Yes, so I am not completely, so I'm not an expert of the solar system chemistry, and I know that there are some studies comparing the volatile abundances in the disks and in the solar system. So so the answer to this question is I don't know, but there's definitely work done there. So I should go back and look at it, and maybe I can provide an answer to this question. But this is definitely a good comparison to make, as it is the planetary system that we know better.
Maybe we can take that to Slack then and discuss it a bit. Maybe also, like in the last talk, to have one question that looks a bit more in the future. What are some molecules that have not yet received too much attention, but that you would like to see in the literature to be studied more?
Yes, so I think CS is one of these. So that's why I put in the paper by Richard Tick, because I think this is, it has a great potential. And in particular, what I would stress is that the strength there was really the multi-transition study. So actually, I wouldn't go for more molecules. I would actually go for like these molecules, but in more disks and maybe in more transition. That was a bit the message of my last slide. So we have that so at least looking at this slide, I'm really struck by the little dots that you see in the bottom part. So this seems very small in the continuum. They are very faint. Many of them are not detected in CO. So I think maybe we won't produce the beautiful images that we are seeing, like the one in HL tau, but I would really like to see these molecules that I've talked about being observed in these much smaller disks that are actually building up like the back population and in the star-forming regions that we have observed.
Yeah. So maybe then we have one last question, which would actually lend itself to have a poll about it. How much of the chemistry in class 2 disks is an imprint from the chemistry in class 0, class 1 phase? And can we ignore that phase when we are modeling class 2 disks?
Yes, so this is, I think it's a $10 million question. And I don't think we have an answer to that yet. There are people working on this link. So mostly people may be looking more at the earlier stages. So how much of the chemistry happening in the younger disks can then be transferred into the class 2 disks. So I definitely think that having a poll could be a good idea. So to see what people think.
Yeah. Okay, wow, that's perfect timing. So with that, we actually came to an end with the review talks. Thanks again, Anna Miotello, for a very lively talk, but also very nicely answering a lot of the chemistry questions here. And the rest you can take to Slack, and hopefully we can have as vivid of a discussion there as we had now. So with that, I hand back to the organizers, and I think we have a short break now.
Yes, there's going to be a 15-minute break, and then that's the end of the invited talks for today. Then we're going to have one of these short presentation sessions like the one we had yesterday. So if you want to know what people have been doing, stay tuned. See you in 15 minutes.
All right, well, we're going to get started. So for all the presenters, remember that you have 1.5 minutes. We have this timer here on the top right. We need to be quickly, so we're not going to be able to wait for you. So whenever the timer reaches 0, we're going to have to cut your mic. So please be quick and specific. Okay, so the first speaker is Eleonora Bianchi. Please, Eleonora, go ahead.
Hi all, I'm Eleonora Bianchi and I'm a postdoc at University of Grenoble, and I'm happy to present you the first results of the FAUST large program together with the other talk of Yuki Okoda. So FAUST is a 50-AU study of the chemistry in the disk envelope system of solar-like protostars, and it's the first ALMA large program entirely dedicated to astrochemistry and a very broad international collaboration. These first results in particular are about the discovery of a hot corino in the class 1 protostar L1551 IRS5 with the detection of several interstellar complex organic molecules. And the main result is that we found that this class 1 hot corino is as chemically rich as younger class 0 protostars. So I will be happy to discuss other details of the work with you, so do not hesitate to contact me. Thanks a lot.
Thank you, Leonora. So next speaker is Justin Campbell-White.
Hi everyone, I'm Justin Campbell-White from the University of Dundee, and in my talk I introduced the Python package StarMelt for the analysis of spectral lines in pre-main sequence stars. The flowchart on the right here gives an overview of the package workflow. It allows you to automatically identify emission lines in high-resolution spectra and match the lines to a reference database. It then fits the models. It fits models to the lines so that from the line profiles you can investigate physical properties of the star, the inner disk, and the accretion. Combining this with time-resolved data allows for variability studies, which reveals the spatial scales for these highly active systems. So I begin the talk with some background on how we utilize emission lines in pre-main sequence stars. I then present a demonstration of the package that highlights its interactivity using Jupyter notebooks. StarMelt is widely compatible with different spectroscopic instruments and data, and therefore has further applications than the emission line tomography we've designed it for. For example, you can select any reference database to match the identified lines to. For more information, please see the talk and get in touch if you'd like to try it out on your own data and potentially collaborate. And for a detailed overview and example applications of the emission line tomography technique, please see Aurora Cecilia Aguilar's talk, which she's introducing later in the session today. Thanks very much.
Thanks, Justin. So next speaker is Maria Jose Colmenares.
Hello, everyone. My name is Maria Jose Colmenares. I'm an undergraduate student in Venezuela. I'm currently working alongside Professor Nuria Calvert from University of Michigan to test the magnetostatic accretion models in low mass young stars. We have used the observations from the X shooter for 37 stars in the Lupus region, studying H alpha, Paschen beta, and bracket gamma lines. We have used the line fluxes from Alcalá, as well as their mass accretion rates. The model is the one picture on the left, so that the magnetosphere truncates the disk and the flows carry the accreted mass. The models replicate the emission lines, and this can vary many parameters as the mass accretion rate, the maximum temperature of the flows, the inclination of the disk, and the geometry, which is described by the inner and outer radius of flows. We have found that the lower accretion rates agree better with large and narrow magnetospheres, large being apart from the star, and stars with higher accretion rates have smaller and wider magnetospheres. Thank you very much.
Thank you very much, Maria Jose. Next speaker is Indrani Das.
Hello everyone, I am Indrani Das from University of Western Ontario. The title of my talk is Ambipolar Diffusion and Ohmic Dissipation in Protostellar Disks. We present a semi-analytic model using linear stability analysis to explore the gravitational instability in disks. we see ohmic dissipation and ambipolar diffusion dominate inner and outer part of the disk respectively. The larger portion of the disk is likely to be mildly supercritical according to the collapse simulations. If you look at the top figure, it shows the peak preferred fragmentation mass occurs at a slightly supercritical mass to flux ratio mu0, and its value exceeds the Jeans mass by a factor of up to 10 based on our model. And these peak preferred fragmentation mass are likely to be around 10 to 80 times of Jupiter mass. The preferred mass for each different mu actually corresponds to the gravitationally most unstable mode that has the minimum growth time scale, tau GM, as seen in the bottom figure. And the tau GM is several times longer than the free fall time for a slightly transcritical mass to flux ratio. So all our results can put a step forward to the understanding of clump formation within the protostellar disk in the early embedded phase. That's a very brief summary. If you want more details, then please watch my talk. Our paper is also on archive. I will be happy to answer your questions on Slack. Thank you.
Thank you very much, Indrani. So next speaker is Kevin Flaherty.
Hello, everyone. I'm Kevin Flaherty from Williams College, and my talk is about our efforts to look for turbulence in planet-forming disks through molecular line observations from ALMA. And going into this work, we expected to see kind of turbulence levels of, say, 20% to 50 or 60% based on theoretical models. But what we've been finding is consistently low levels of turbulence, starting with HD 163296 and TW Hydra, and going on to more recently MWC 480 and V4046. But we did recently find one kind of detected level of turbulence around DM tau, about 28% of the sound speed, shown on the right there. And we're now following up these observations with N2H+, the student working on this, trying to use this more optically thin molecular line tracer to get at what's the turbulence closer to the midplane of the disk, combine that with our constraints on the turbulence in the upper layers of the disk to try to understand what's the vertical structure of the turbulence, which can tell us something about the physical model that's driving the turbulence in this system. Following up on that as well, since DM tau stands out as the only one with detectable turbulence, what's unusual about this system? I've been looking at IM loop recently. Because it has a young age like DM tau, and unlike a lot of the other sources we've looked at, but that one seems to have low turbulence as well. So it seems like age is not kind of the only factor setting the turbulence level. So that's kind of the results so far. So follow the talk to get more, and thank you very much.
Thank you very much, Kevin. Next speaker is Antonio Garuffi.
No, I think we had a casualty. He just, his connection dropped. So we're gonna move on to Sierra.
Sierra then.
Hello, all. My name is Sierra Grant, and I'm a graduate student at Boston University, finishing up my PhD. My talk is an ALMA survey of disks in the star-forming region LIN 1641 in the Orion Molecular Cloud A. This region has over 700 class 2 disks, of which we observed 99 in this survey. This region also has great coverage in cycle 7 by Van ter Viska and collaborators, so I hope you also see his talk. On the left, I'm showing our sample distributed throughout the L1641 filament. On the right, I'm showing the cumulative dust distribution. You can see the L1641 protostars from Van Dam in blue. Below that is our sample of class 2 objects in dark gray. And then below that, you can see these other really great class 2 surveys in other star-forming regions. We find relatively massive disks. However, our sample is biased towards these more massive disks, and I discuss that more in the talk. On the bottom, I'm showing one object that shows large-scale structure in the dust and all 3 gas lines. We think that this could be potential envelope emission. There's been a lot of talk on this on the Slack channel, and I'm happy to discuss that more there. Thanks so much.
Thanks, Sierra. So let's go back to Antonio. I think it's back now.
I am here. Can you hear me?
Yep.
Yeah. Okay. So it's also 5 years after the first VLT Sphere GTO results. So I thought to summarize actually what we have obtained these years. We have observed more or less 60 protoplanetary disks, which is a relatively large number since it's actually a half of the total number of disks ever imaged in scattered light. And we'll cover the relatively large parameter space from 0.3 to 3 solar mass stars, any kind of age within the Permian sequence phase. But we are still a little bit biased toward massive protoplanetary disks, and we are trying to alleviate this biasing by imaging less and less massive disks. We have had a very good synergy with ALMA, with a direct comparison between ALMA and sphere images showing that when we have a cavity from ALMA, this may or may not be seen in sphere, although this can even be smaller. And we saw that when we have rings from ALMA, these are typically there in sphere, whereas when we have spirals from sphere, these are not seen in dust continuum images, but they are actually seen as azimuthal asymmetries in the ALMA images. And finally, we see recurrently shadows from the disk surface. There are very good proxies of the geometry of the very inner disk that we're trying to investigate now. Thank you very much.
Thank you very much, Antonio. Next is Meryl van Hoff.
Yes, hello, my name is Merel van het Hof. I'm a postdoctoral fellow in the Michigan Society of Fellows. So with evidence piling up that the first steps of planet formation already start when a disk is still embedded in its envelope, it's becoming clear that class 0 and class 1 disks provide the true initial conditions for planet formation. However, these young disks are not yet as well studied as more evolved protoplanetary disks. And so the question remains whether their physical and chemical structures are similar. So for example, protoplanetary disks are observed to have a large cold region where CO is frozen out, as shown in the top of the cartoon. And to construct a global temperature profile for these young embedded disks, we observed two molecules with different freeze-out temperatures, C17O and H2CO, toward a sample of 5 class 1 disks. And particularly good targets are edge-on disks because they allow you to probe both the radial and also the vertical temperature profile directly, as shown here very beautifully for IRAS 04302. So in our sample, we see no signs of CO freeze-out at radii smaller than 100 AU, which is in contrast to Titori disks, where the CO snow line is located at a few tenths of AU. H2CO freezes out at 70 Kelvin, and its emission comes from the surface layers and not the midplane. So these results show that young disks are warmer than protoplanetary disks, and hence planet formation may start warmer than we generally assume. Thank you.
Thank you very much. So next speaker is Margot Limker. Please, Margot, go ahead.
Hi, my name is Margot Limker, and in my YouTube video, I'm looking at one of my favorite topics that Anna Miotello also highlighted in her review talk. I see conditions in protoplanetary disks, how and where to find your water snow line. And the water snow line that you can see in the cartoons on the left and behind me is very important for planet formation, but it's hard to trace directly. And HCl Plus provides a solution because it's mainly destroyed by gas phase water. Therefore, we expect a drop in the HCl Plus emission in the inner regions where water is in the gas phase. And the main result that I would like to share with you right now is that we used HCl Plus observations in the outbursting source V83 Ori to locate the water snow line. And these observations that you can see on the right show a drop in the HCl Plus emission in the inner parts, which is partly due to water sublimation. And our analysis is consistent with a water snow line at approximately 100 AU, which you can see with the black arrow and the orange line. And that also means that it's unrelated to the water snow line, that the water snow line is unrelated to the abrupt change in the continuum observed at 42 AU that you can see with the blue line. I'm happy to answer any questions that you might have, and hope to see many of you there virtually. Thank you.
Thank you very much. And sorry to you, Margot, and to Neville. I think I just destroyed both your names with my pronunciation.
Don't worry.
Next is Ezequiel Manzo Martinez. I know this pronunciation better.
Hello, I am Ezequiel Manzo, and I would like to encourage you to watch my talk. And in this work, we perform a statistical study of the innermost regions of protoplanetary disks in various nearby stellar groups, ranging from 13 megayears, using a new indicator of infrared excess in the IRAC and MIPS 24 bands. We find a clear decreasing trend of the infrared emission with age in all bands, which suggests evolution in these inner regions. We also determined mass accretion rates and found a decay with age that is consistent with viscous evolution. Moreover, using a large grid of irradiated disk models together with Bayesian methods, we reproduce the observations and find highly settled disks in our sample even at 1 megayear. Also, the fraction of these highly settled disks increases with age. In addition, we estimate a photoevaporative wind mass loss rate that fits reasonably well the decay of the disk frequency and the fraction of accretors with age. And finally, we show the curved shape and inward evolution of the different snow lines. So please have a look at our published paper, and I hope you find these results interesting in the context of the very nice talks that we have heard today. And I would be very happy to discuss these results at Slack. Thank you.
Thank you very much, Ezequiel. Next is Nienke van der Marel.
Hi everyone, my name is Nienke van der Marel and I'm a Banting Fellow at University of Victoria. So in my talk, I present a recently submitted paper by myself and Gijs Mulders on disk demographics connecting with exoplanet demographics, where I took the results of all these beautiful ALMA disk surveys together and classified each disk according to their morphology. So either a transition disk, a ring disk, and then for all the disks where we basically don't have high resolution data, I simply classified them as either extended or compact, so depending on their size. And what we see is that the structured disks and the largest disks essentially retain their dust mass if we look at older ages, whereas all the compact disks lose their dust mass. So we can understand that if structured disks contain pressure bumps, whereas all these compact disks are non-structured and are dominated by radial drift. And then we can take this a step further by looking at the stellar mass dependence of each of these morphologies, which we see on the right. We see that higher mass stars have many more disks with structures. And coincidentally, that is the same for the giant exoplanet occurrence if you correct for detection biases, which is what Gijs Mulders has done. So we think that these results indicate that structures in disks really must be linked to giant planets. And for more details, take a look at my talk and feel free to ask me any questions.
Thank you very much, Nienke. So next is Arnaud Michel.
Hello, my name is Arnaud Michel. I'm a first-year graduate student at Queen's University. And in my talk, I discuss bridging the gap between protoplanetary and debris disks. And this work was also done with Nienke. And so it was done in parallel, but we retrieved some similar results where we find two disk evolution scenarios. One where radial drift dominated disks, so this would be more or less equivalent to more compact disks, become diskless quite fast. And then the structured disks, so ring and transition disks, are the possible progenitors to cold debris disks. And so here on the bottom left, we have a dust mass, a millimeter dust mass plot as a function of fractional disk luminosity for various protoplanetary disks in the class 2 and class 3 phase, and then debris disks. And what we can see is that essentially during the class 2 phase, two processes are actively taking place, namely radial drift and dust growth, which are decreasing the dust mass, and then the disk dissipation and evolution is gradually taking place and decreasing the fractional disk luminosity, removing these disks. And what stands out is that the structured disks have much higher disk dust masses for a wide range of fractional disk luminosities. And so it begs the result and the connection with the cold debris disks. Thank you.
Thank you very much, Arnaud. Next is James Milley.
Hi everyone, I'm James Miley. I'm a fellow at the JAO Santiago with NEAJ, and my talk is on my recent paper coming out this month, exploring the impact of stellar evolution on the protoplanetary disk. So the protoplanetary disk hosting stage of a star is also a phase in which the stellar properties, such as the luminosity, are evolving quite significantly. And the way in which they evolve depends on the mass of the stellar object. So low mass stars evolve differently to intermediate mass or high mass objects. And these evolving stellar properties will have implications for the disk that the star is hosting. Primarily, the evolving stellar luminosity directly impacts temperature in the disk, which in turn plays an important role in setting the composition throughout the disk, so determining the materials for planet formation. So we now have an ever-increasing amount of information about composition of directly imaged giant exoplanets, such as these we are regularly invoking to carve the gaps and the rings we see in our images. Our study looks to determine to what extent we can constrain not only where in the disk, but when these planets are likely to have formed based on the C/O ratio of the planet and the disk it formed in. So that's what this figure is here, where we've applied it to the system of HR 8799 with multiple directly imaged giant planets in it. And our modeling suggests that planet B must have formed at very early times in the disk's history, so towards the class 0 or class 1 phase. So if you're interested, please check out my talk and please do get in touch. Thank you very much.
Thank you very much, James. Next is Dhruv Millet.
Hello, everyone. My name is Dhruv Millet, and I'm a post-bac research assistant at the University of Victoria. And the talk I've made for 5 years after HL Tau is one where we look a little bit more closely at transition disks. So it's based on a couple of previous works I've been involved in. So in some work we did in 2019, we found eccentric superjupiters are capable of carving wide transition cavities. Now, this has been out for some time, but one point we didn't really focus on at the time is that transition cavities carved by this process actually have a wide separation between your optically thin gas cavity, which you'd see in 12CO or another tracer, versus the outer dust ring, which you'd observe in millimeter continuum. And it turns out, with some recent work led by Nienke van der Marel that I was also involved in, turns out that there are a lot of systems, transition systems, where we found this wide separation between the gas and the dust cavity. So, and in fact, one way to explain it is you just have very, very massive planets, but it turns out that the occurrence rates of these massive companions, brown dwarfs in fact, are not high enough to explain the abundances we observe. So we come to the conclusion that perhaps many of these transition cavities are indeed carved by eccentric superjupiters. So yeah, thanks for listening. I encourage all of you who are interested to watch the talk and post any questions you might have to the Slack.
Thank you very much. So next is Álvaro Rivas.
Okay, hello everyone, I'm Álvaro Rivas. I'm an ISO Alma Fellow in Chile, and in this poster I'm presenting the work we did combining the D'Alessio irradiated accretion disk models, which are physically motivated models which use the alpha disk prescription with a large sample of disks. So as many of you know, the problem with this type of detailed models is that they tend to take a lot of time to compute. In the case of these models, it's 1 to 2 hours each. So it's unfeasible to use a Bayesian approach if you want to do this with a large sample. So we use artificial neural networks to speed up the models. Now they take just a few milliseconds to run, and we were able to fit 23 disks in Torus. And from the posterior distributions, we got a few interesting results. One is that we get a lot of high viscosity values in contrast with recent observational results. So with this kind of points that maybe the alpha disk alone is missing something. Maybe disk winds are crucial for understanding of disks. And also, as mentioned during the invited talks today, we also get dust masses that are a factor of 3 times higher than the one from millimeter surveys. So maybe we are underestimating masses from submillimeter fluxes alone. If you want to know more, please check my poster, the paper is out, or come talk to me. Thank you.
Thank you, Álvaro. Next is Annalise Rillinger.
Hi, everybody. I'm Annalisa Rillinger. I'm a graduate student at Boston University. My work focuses on the disks around brown dwarfs. Specifically, I use radiative transfer models to fit models to the spectral energy distributions of these objects. And we do that in order to constrain the disk masses, as well as to look for evidence of substructure in the disks. So we've compiled a sample of 48 brown dwarfs, which is the largest sample of brown dwarf SEDs to date. The objects come from 4 different star-forming regions, Ophiuchus, Taurus, Lupus, and Upper Scorpius. And so since these regions have different ages, by computing all these disk masses, we can get a sense for how brown dwarf disk masses change over time. I'm showing 2 example SEDs on the left, just so you can get an idea of what our fits look like. All 48 objects have millimeter data, so that helps us constrain the disk masses pretty substantially. On the right, I'm showing an example of one of the objects for which we find evidence of substructure. So this object was found to be best fit as a pre-transitional disk. So it's pretty exciting that we're seeing substructures in brown dwarfs as well as around stellar objects. So if you're interested in brown dwarf disks, please check out my talk and feel free to reach out on Slack. Thanks.
Thank you very much. So next is Sal Rother.
Hi, I'm Sahal Zauter. In my talk, I will be speaking about some of our recently published work where we investigated the impact of planet-disk interactions on the structure of gravitationally unstable disks. We show that a planet causes the large-scale spiral structures present in self-gravitating disks to be suppressed such that they appear largely axisymmetric with a ring and gap structure. The interaction between the planet and the disk essentially shortens the gravitationally unstable phase of the disk. We present mock ALMA continuum observations which show that in the absence of a planet, spiral arms due to gravitational instability are easily observed, whereas with the planet, no large-scale spirals are seen, but instead a gap and ring structure is present. We also show that the planet's presence can be inferred by its spiral arms in the continuum observations and by the deviations it causes in the disk kinematics. Our work shows that high mass disks can also appear axisymmetric, and we discuss some of the observational implications of our work. Thanks.
Thank you very much, Sal. Okay, next is Aurora Cecilia Aguilar.
Hello, so I'm Aurora Cecilia Aguilar from the University of Dundee, and my talk is about what you can do when the things that you're interested on are a bit too tiny to be directly resolved, such if you want to know about accretion, or you want to know about winds in stars, or you want to know about the connection between the inner disk and the magnetosphere. So then you are dealing with processes that are very hot, so they may be producing in the optical, and then they are also very rapidly changing. They have short time scales. So there is a time where you can do time-resolved spectroscopy and photometry to see what is happening. In my talk, I'm giving a couple of examples of what we have seen so far. We have seen for the disk of J1604, how accretion can actually drain the innermost disk in timescales of days, and also how you can see bigger changes in timescales of years when you don't see any accretion, when you don't see any eclipses, when you don't see any inner disk that may be related to something living inside the disk. We also have done CCMA, which is a massive star where you can see actually layers of the inner disk, different depths in iron lines, and you can also see a variable winding wind that appears on the star. You can also trace accretion because you have many lines. You can derive temperatures, densities, and the spatial structure using the time. It's very hard to deal with so many lines, but Justin Campbell-White, who was presenting just before, has constructed a wonderful code in Python that allows you to analyze that. So if you want to learn more, please come to our talks. Thank you so much.
Thank you very much, Aurora. Next is Dimitris Stamatelos.
Hello, this work is motivated by observations of giant planets around M dwarfs. These planets are very difficult to form by core accretion, so we examine the theory of gravitational stability. So there are systems where you have a 10 Jupiter mass planet orbiting something like a 100 Jupiter mass M dwarf. So that tells us that the initial disk from which this planet formed was at least 10% the mass of the central star. And such massive disks are prone to disk fragmentation, to gravitational instability. So we performed an ensemble of about 30 simulations and tried to find out the properties of the fragmentic disks and also the properties of the planets that form. So we found that really high disk to stellar mass ratios are needed for fragmentation to happen. about 30%. And we also determined the properties of the exoplanets produced by this mechanism that are shown here. And we try to compare them with the observed properties of exoplanets around M dwarfs. For this, we need to do a little bit of more work to see how this planet evolved from their initial conditions, from their initial properties to the final properties after they evolve within the disk. So for more information, please see my talk, and I'll be happy to answer any questions. Thank you.
Thank you very much, Dimitris. And now we'll have Dimitris. I'm sorry, Timmy, who was here.
Yeah, thank you so much. Hi, guys. My name is Timmy Delage. I'm a PhD student at MPA working with Paula Pinilla. And in this talk, we want to study the impact of diskization on disk morphology. So to do so, we developed a code that's like a Python-based code, which is called mhdpy. And basically, you can see this code as like a bridge between a diskization level and basically how the dust are distributed across the disk. So what we do is like you set any star and disk properties, you input this into our code mhdpy. This code can give you like two different alpha parameters. One alpha parameter that can describe more self-constantly the turbulence felt by gas and small dust particles in the red profile, and the blue profile that will be more consistent to describe the turbulence felt by large particles. And with those two alpha parameters, you can constrain different dust and gas transport mechanisms. So the gas viscosity, dust settling in the red, and the dust turbulence and radial diffusion in the blue part. And then you can run your dust evolution model. In this case, we use the dust evolution model called DustPy, which is a 1D dust evolution model. And you can get those kind of like cool dust distribution, radial dust distribution across your disk. So if you want to find out more about the method that we use and the approach, please feel free to watch my talk or email me or both. Thank you so much for your attention. Bye.
Okay, so that's the last presentation of today. I want to thank all the invited speakers and Inga, the chair, for great talks. We hope you had fun, and we'll meet tomorrow. Remember that the session tomorrow starts 2 hours early. Thank you, and have a good one.